Hey, welcome to the most in-depth DevOps course on how to go from never using the cloud to getting your first entry-level role. I'm sharing the things that I've learned as a site reliability engineer in a large managed service provider where we manage over 5,000 virtual machines across 50 plus clients. And I've made this course along with other tutorials on my channel just to help you grow your career. Before we get started, just go ahead and bookmark this video so that you can come back to it later and reference it. And so in this video, we're going to go through everything you need to know about Git, GitHub, and GitHub Actions. We'll go through AWS common services and what their use cases are. We're going to go through Terraform. We'll go through the basics of networking. We'll go through Docker, Kubernetes, deploying with Gitops, and then writing your first Ansible playbook, and then monitoring with Prometheus and Grafana. There will be timestamps in the description so you can jump around to what's relevant to you. Okay, so we're going to start it off with Git here. This game's a great visual to get an understanding of how commits work and how branches work. So if you're already an expert on branches and commits, feel free to skip ahead, but if not, this will be a great representation. I'll leave the link in the description to learn gitbranching.js.org if you want to try this out yourself. First, let's assess what we have. We have commit 0 through 7, and then we have 4 branches. We have bug fix, side, main, and another. And we're currently on side, and that's denoted by the star here. So what I want to do first is let's go ahead and catch up our side with our main branch. So I'm going to do git, I'll do git branch to make sure I'm on side. And there we go, the star again by side. So I'm going to do git merge main. And now you'll see we just caught up. So we merged our main branch into our side branch by running that command. Now let's go back to our bug fix branch and check that out. So I'm going to do git checkout bug fix, and now you'll see we're back up on this commit. If I want to do a commit from here, since there's already commits ahead, we would need to handle these or we would fork. So I'm going to do git commit, and you'll see here it's going to create a new fork from that branch, and our bug fix is now on that commit. I'm going to skip that. I'm going to come down to git checkout main. And real quick, these commands, like the git checkout and git commit, there's not any context to these because it's just for the game, but it gives you a really good understanding of what's happening when you run these commands and how the branching flows. We're going to check out side, and then I'm going to do git commit, and this would be like my feature branch. So now I'm on side. So hopefully that quickly gave you a good understanding of how these branches work and how commits work in Git. Now that we're back in our terminal, let's put some of that knowledge to use. So I'm going to cd into that repo that I cloned, and this is called DevOps Bootcamp. Do ls, you'll see that it's empty, and do git branch, and we'll see that there is just the main branch right now. So I'm going to go ahead and check out a branch that's called demo for this video. I'm going to run git status, and this is going to show what files we currently have and what's untracked. So we'll see here main.py and secrets.txt are untracked. So if we run git add main.py, then it's added and we can do status, and there we go. But the problem is we don't want to add secrets, and we want to make sure we don't accidentally add it or have someone else add it. We need a way of preventing it from being tracked at any point. To solve this problem, we're going to use the git ignore file. So this repository from GitHub shows us some common git ignore files. So if I scroll down to the python.gitignore, you'll see it catches all the common files that are in a Python directory and make sure that they're not committed. So what we want to do here is avoid checking in secrets and avoid checking in files that are too large for Git to handle. For my setup here, I'm going to go ahead and create a .gitignore file, and it needs to be exactly named this. And then I'm going to open up that file. And this is in NeoVim, if you're wondering. And what I'm going to do here is do star star secret star star. So this is basically saying any file with the name secret in it, do not add it to Git. Save that, do ls quickly. Now when we run git status, we will see that our main.py file is still there, and we have our git ignore file being copied in, but we do not have the secrets file. So this is perfect. I'm going to run git add dot to add everything in my working directory. Run git status again just to show, and now it's adding these two files, and I'll do git commit hello world. And then last thing, I'm going to go ahead and do git push. This is going to fail. I like to just copy this command. So since it's the first push of this upstream branch, we're going to have to copy this command. And there we go. Next, if you come back to your GitHub, you'll see that there's this little flag here. Demo had recent pushes 2 seconds ago. So before we click on that, I'm actually going to go and open the branches here. And you'll see we have our main branch and then we have our demo branch. And our demo branch is one commit ahead, if you remember back to the visual representation. A general good practice for branch management is that you'll have a main branch, which is the default branch, and then you'll create feature branches off of that. I might have a branch to add a new button change or adding a new API endpoint, those sorts of things. In infrastructure, the most often way that I've seen it is that we have two other branches. So we add a main branch and then, sorry, we add a dev branch and then we add a prod branch. And so now changes get merged from whatever your branch is into dev and then into prod. So in this case, I'm going to go ahead and do compare pull request here from our demo. We're going to merge this into our main branch and you'll see we add a title and then a description, initial hello world. And then I press create pull request. And now that this is created, you'll see it checks for ability to merge and everything's good here. So I can go ahead and merge pull request. The next thing we're going to do is add in a linter for our CI/CD pipelines when we trigger pull requests. So these are always going to live under .github/workflows and then your file name, and it's going to be a YAML file. And so this is going to be linter.yaml. And if we come over to this URL, I'll have linked in the description. This is a super linter. So it lints basically everything you can imagine. If you're not familiar with linting, it's just making sure that the syntax and the structure is proper. So if you scroll down in this page, you can actually copy this file. And I'm not going to go too in depth into how this file is structured here because I have another video that I'll link on this, but we will go through the basics of this and when these are used. So if I come back to my VS Code, I'm going to go ahead and paste this in here. The main thing here is that we're going to trigger it on push and on pull request. That means that whenever those actions happen, this should run. And then down here, we're going to run the superlinter job, which is the one we just pulled from GitHub. So now if I save this and push it, and I'm going to commit this to my main branch directly. Oop, I actually need to pull. Okay, so this is a good point. There was the secrets here. I saw it was going to be added, and that's because I'm not up to date. So if I press this circle down here, if you're using VS Code, it will pull it. Or from the CLI, you can just run git pull, and it'll make sure that you're up to date. So we're up to date. I'm going to add linter in my message. And using VS Code here is the same. What I just did is I just did git commit -m with linter as the message, and then I did git push by pressing the sync button. If we come back over to our GitHub, we should see that we have a new push on our main branch, and there we go. And now, because we pushed, see this little orange circle? That means that we have CI/CD pipelines running, or GitHub Actions as they're called here. So if I come up to the Actions tab, and now here's our linter. I can open this up and then open the lint job. And what this does very quickly, it's pulling a container that we've predefined, or pulling an image rather, and building a container from it, and then running the job that we set up. While this is running, we're going to actually go into open a pull request now. So this would be our promotion process from main going into dev. So say I just added that feature of linting to main, and now I want to promote it to our dev environment. And here we go, I open pull request. This time you'll see this linting file added, and then the git ignore and the main, all because dev was made off of the prior main branch. So I'll do create, promote to dev, and I'll put adding a linter. Make sure that your messages are more fleshed out than this if you're in a production environment. But this looks good for now. I'll do create pull request. And now I want to talk about approval flows. So what needs to happen before we can go to dev with this? At a bare minimum, you should be having some other person review your code. In some environments that have strict compliance requirements, they actually require that the code is reviewed and that at least two people have their eyes on this code. I can't do this by myself, unfortunately, but if we open up files changed, I can show you how it would be done. So you open files changed, here's everything that we just committed and what's going to be happening in our dev branch from main. You can come over here to the right and do review changes, and there's three options. So we can comment and just say, like, this is okay, but I might have done this differently. I can do an approval, which is an actual approve saying, this looks good to me. So usually it's done like this, LGTM looks good to me.
And then the last thing would be request changes. So if there's something that you're like, hey, this cannot be added in here, you would leave a comment, say, go check this line, request changes, submit review. In this case, I'm just going to do a comment, but this would be like an approval saying this is fine with me. And that is one of our checks to make sure we're good. The other thing that you should have is the CI/CD here. So we want to have checks running before to make sure that we have testing going into it. And then after we actually deploy to dev, let's test it there. Next on the list, we want to talk about our rule sets. So if you come into settings, go to rules and then rule sets, we can actually configure rules on our branches. So if I do a new rule set here, let me actually go back. I think I did that. So new rule set, new branch rule set. And then I'm going to call this PR required. So PR being pull request. And I'm going to make it enforced. And then let's set it on down here, branch targeting. So you can do add branch. I could include all branches, but I don't want it on main in this case. So I'm going to do include by pattern. And I'm going to set it, I'm going to just do it on prod for this demo. Add inclusion. Now that means that we cannot go to prod unless we have our rule set in place. Now, if we come back to our pull request, we're going to see the big X there because our job failed. So our linting did not work. But for this demo, I'm going to go ahead and move forward. So I will merge the pull request. So now we push our changes to dev. I'm going to go ahead and push them to prod or open a pull request to do so. So I'm going to press compare and pull request. And this is going into main. So I want to do dev and then the arrow going into prod here. And I'm going to name this promote dev to prod and create pull request. And then it's going to trigger our checks. And so now we can wait for this linting, but for this demo, I'm just going to go ahead and merge it. And that would be the full life cycle of our code going from feature branch all the way into our prod. If you remember back to the visual earlier, this is where we just caught up all three of our branches to the same commit as of right now, main, dev, and prod. The next thing I want to discuss is secrets. So if you come into settings and then come down here to secrets and variables and then actions, from this menu, you can set secrets or you can set variables. So I'm going to set a new repository secret and call it AWS. I'm just going to call it AWS key, and then I'll set it to my key. And then you can press add secret. And then this key can now be referenced from my build pipeline in my GitHub action. So this is just a linter, but if this was, say, building my Python server, I could set my API tokens inside of that build so that I have it available there. The way you'd reference that, similar to down here, I would do AWS key equals and then secrets.aws key. So this one's predefined by GitHub, but this is now our custom secret that we just created.
That wraps up GitHub. Next up, we're going to move into an architecture design session where we're going to take a 3-tier architecture on AWS EC2 instances or just any kind of server and show all the different ways that we can deploy them using common AWS services. This is that traditional 3-tier architecture. So you can see we have our VPC up here, and then we have 3 different subnets isolating our interface, our application, and our database. And then our user will come in, they'll reach the interface layer that will interact with the API, and the API will make calls to the database as needed. Very simple. This is usually what you're going to get when you are migrating either your first time on a cloud service, or if you're just moving from an on-premise site and you just have to move things as quick as you can, and you were running servers on-prem, so now you're going to run servers in the cloud, but nothing else really changes. This is like the easiest to get going if you've already had the stuff built out on VMs, but it's really not the best approach. We don't have any kind of auto scaling, so it doesn't matter if we have 0 users, we're going to pay for all 3 of these instances. But also, if we have very fluctuating traffic where our users are going to spike a lot at peak times, we have to build our instances at the level that can handle that peak capacity and have them running all the time. So this is very rigid, and we don't get any flexibility in our cost, which that's really the whole benefit of the cloud. It's that we're able to pay for what we use, not pay for stuff that's running all the time and not being used. So with that being said, let's go ahead and introduce some auto scaling groups so that way we can get some of that flexibility that we're looking for. We can introduce them, one on each tier of our application, and then we can set a minimum size, a desired size, and a maximum size, so that way we can scale as our traffic comes in. So we'll need a monitor to know our usage, But if we can see that our CPU and our memory usage is at 20%, then we should probably scale down. Say we have 4 instances, let's scale back to 3. And if it still stays low, let's scale back to 2. But if we set our minimum size to be 2 instances, then it'll never go below that just in case users come in quickly. And that being said, in this scenario, we have 4 instances being our minimum size, but desired, we try to stay at 6 when possible. So that's really where we should be most of the time. But we have a maximum size all the way up to 12. So that way, if we have traffic at peak times that we need to handle 12 instances, but that's only 1 hour out of a week, then we can set our maximum size there. But then the rest of the week, let's scale down to 6 so we're not paying twice the cost. So these auto scaling groups will give us a little bit more flexibility in our cost, because now if our peak workload requires 12 instances, we don't have to always run that peak workload. We can run 6 most of the time and cut down our costs that way. But it's still really not the best approach. It's pretty difficult to manage this at scale, and we have to make sure our VMs are set up in a way that we can configure them on and off, which it's good because it gives us that reliability. If one VM breaks or goes down for any reason, we can just spin up another one automatically with our auto scaling group. But that being said, there's a lot of work up front that goes in to get all of this in place and working properly, making sure we have the monitoring ready to track our CPU and memory usage and know when we should be auto scaling. So there's still a lot of work that goes into this, and it's still not the best solution. So with that being said, let's look how we can containerize our application and get a little bit more flexibility in our scaling. So the next move we're going to make is we're going to move to AWS ECS, which is Elastic Container Service. This is going to allow us to containerize our application and then deploy it on a cluster. So we can create an ECS cluster that then scales as our users come in. So we move the application and the interface layer to this cluster. And because we're using containers now instead of VMs, when the VM starts, it has to spin up the operating system and install all the dependencies that go into that. Whereas the image is already pre-built with those, and we can spin it up in seconds. So we go from creating a new AWS EC2 instance that takes a couple minutes to just a few seconds for containers, which makes that scaling so much faster. And we can get a more accurate representation to what our current user workload is with these containers rather than the EC2. And the other benefit is that now we don't have to manage the EC2 instances. We don't have to make sure they're patched and up to date. We don't have to go in there and make changes or set up our deployment pipeline there. We can just create a container, and we know that wherever we want to deploy this, whether it's ECS now or if we want to make changes to our application infrastructure in the future, like say move to Kubernetes, then it's still a container. We can deploy it wherever we want, even if we want to switch cloud. So this is much better because we have this scalability that we're looking for now, but it's still not great. So the downside here is that we are adding complexity in some sense. That is absolutely true. You have to now create an ECS cluster that you are managing. So that's going to take someone that is experienced in this area. You're going to have to know how to package your application and your interface as Docker images and deploy them to, say, an ECR repository to be pulled from here. You're going to need some kind of container security pipeline, maybe your build pipeline from your GitHub action to deploy here. So there's complexity in all of this, but this definitely shifts the complexity. If you're not familiar with it, it can have some problems. And the other thing is that it's still higher cost. We still can't really scale to 0 if we don't have any users at the time. Like say our application's only running during the day, then we still have our database running all day long on an EC2 instance. Our ECS cluster has to have at least one container running at all times so that if a user does happen to come in there, it's ready to go. So there's no scale to 0, and if our application needs to have that, then we don't have the ability to do so. So the next change we're going to want to implement here is we're going to go ahead and put an Amazon API gateway in front of our API. And then that API gateway will manage the access, both the access control and the request to our APIs, and we'll move our APIs to Lambda functions. So with our new setup, we can now scale out our Lambdas, and each Lambda will be its own self-contained function. So we might have a function that says get users or get data, whatever our APIs are. Each Lambda function can be its own API, and this is that traditional microservice architecture that usually goes with cloud native applications. So now our front-end users will come into our service, and say we authenticate them with a Cognito user pool, then we know that the user is who they say they are, and then within that Amazon API gateway, we can know that that user is authorized to access the resources, and we have their identity. and then they can invoke the Lambda function, whichever APIs it might be, and it returns back to the front end. And that way, only the Lambda functions are inside the VPC with the database. So that's the only way it can be accessed. You can't access it publicly, but then the users are able to hit those APIs and get the response back that they're looking for. So this is great now because we have that flexible cost in that if no users are using our API, we're not paying. We do have to pay more on invocations. So the downside here would be if you have an application that has hundreds of thousands of users and you're paying per invocation, those costs will rack up quickly. But if this is a smaller app that most people watching this video probably are running, then you're able to scale to zero now. So you pay for what you use and that is it. And hopefully your revenue is tied to the amount of users that you're having. So as you get more users, your revenue should more than cover the costs of these. And so that approach is great. Let's now do similar with the front end. And the way that we're going to do that is we're going to move from that ECS containerized image to a fully static web app. So AWS and other cloud providers allow you to run these static web apps from just a storage account or an S3 bucket. If we're using something like React, we can create an optimized build that is just a static list of files and then host them on an S3 bucket. So it's extremely cheap because we only have to pay for the storage and the transfer of data. So as users come in and request those files, which is how they view it, then we only pay when they're using it. And otherwise, you're paying basically nothing because your files are so small relatively. And so the way that this is going to function is that we'll create an optimized build that is hosted on S3. That'll list out our files. It's usually an index.html that points to your other supporting files within that build. And the user, and so then the server, and so then we don't have an interface server. It's all on the client side. So I, as the user, might go to your website and request the files necessary to view, and this S3 bucket is going to send me those static files that are then built into HTML, and I can view them directly from my client. Then from my client, I would make requests directly into the application server. And then lastly, you'll see here this CloudFront. CloudFront's a globally distributed CDN, or content distribution network. This allows us to cache our responses so that way it can reach the person faster no matter where it's at. So if I host my S3 bucket, say in US East 1, that's going to be probably somewhere in Virginia. And if I have a user in Europe, they have to request those files from Europe all the way across the globe to US East. So that's going to cause some latency problems if they're requesting constant content. The other thing is if I'm a user and I just keep refreshing the page, we have to just keep sending data if we don't have a CDN. Whereas if we put the CDN in front, when a user requests data, it'll actually store that latest data in the CDN that's closest to them, and it'll only send them that unless there's a change. So I'm on the West Coast. If I request content from the East Coast, what happens is I'll hit the CDN, and then from the CDN will pull into the S3 bucket and pull the content back to the CDN and then pass it along to me as the user. And that will allow me to have a faster response because now every other user on the West Coast that has to reach out to the S3 bucket, they're going to hit the CDN or the cached content on the West Coast already, so it's quicker response. And the other benefit is that if we have 100 users all sending the same request at the same time, we only have to grab it from our S3 bucket once, and then we can just send the cached content to the user. There's some tricky things here, like you have to set a TTL or time to live, so your content isn't just cached indefinitely, and if you make changes that it's going to be pushed, and you can also invalidate changes. So if you're looking into using this, look up those things to make sure that you have content that is not getting cached and you're not able to push changes because of that. But generally the CDNs handle this pretty well by themselves. But you probably want to have a CDN in front of your application in almost every circumstance, whether you're doing with the S3 bucket or this could apply to the prior interfaces, whether we're using EC2 or an image on ECS. Whatever your application's running, you can just put a CDN in front of it, and that will generally help your user experience. So I'm pretty happy now with our infrastructure on the front end and the API because we have that static content that is only used as users come in and use the system. But we still have the elephant in the room of the database server. I don't think anyone watching this wants to be running their own database on an EC2 instance, managing the patching and the updates of the server, along with the updates of the database. So let's look into some AWS managed services that can offload some of that work for us. For this example, we're going to go with Amazon Aurora. Aurora is the fully serverless SQL database that Amazon offers. So if you're running a SQL database, you generally want to go with this and you want it to be serverless. But I wanted to also shout out DynamoDB. So if you're running a NoSQL database like a document store such as MongoDB, DynamoDB will be your better option there. It's a key value store database and you can set up all of your own. And it's usually better for very small kind of thrown together applications. But if you want to enforce that type and that schema, then Aurora will be the choice for you. Both of these services will scale automatically on a pay-as-you-go model, but if you're looking for more complex queries, then use Aurora, whereas DynamoDB will offer you speed of building, but it does limit you in some of the join capacity. And generally, running these efficient, scalable databases that are again pay as used, it will help lower your cost as well as reducing the need for someone that is a database admin. So you might be paying more for this versus an EC2 instance depending on your usage. So you might be paying more for Aurora or DynamoDB than you would for an EC2 instance running your own server. Just the actual cloud bill cost. But when you bring into account the cost of paying a database admin or some kind of IT sysadmin to manage your database, the access to the database, the updates to the database, the scaling of the storage, as well as IT sysadmin that can be able to patch your server, those costs are going to blow this out of the water very quickly unless you're running a huge application. So this architecture looks great so far, but there is one other downside that I want to discuss. If you're running an application that has a lot of traffic and or has asynchronous request needs, then you're going to want to look into something like Amazon SNS and or SQS. So SNS is one place published to all, whereas SQS is one place where SQS is multiple things that publish to a queue, and then that queue goes to one place. So why might we need those? In the case that we're going to be doing a lot of queries, and especially if they're long running queries, we need a queue to make sure that our traffic gets handled. Say we need to enforce a first in, first out, or a FIFO order, then we need some kind of queue to maintain that traffic and ensure that it's happening in order and that we don't miss any requests. Like, what if we get a huge flux of traffic in and then our database can't handle it and we just can't respond with data to our users? That would be extremely bad for our application, which it still would be bad to have a slow response time, but let's at least get them a response. And if it's something asynchronous, like I'm going to run a query and then I get an email later in the day with all the results of a PDF file that I'm looking for, then that's even better because let's just throw it in the queue. We'll make sure that queue happens, and then we'll send out the user a notification later in the day when it's ready. Here's the final design that we're looking at. So we have our users coming into our system. Their first touch point is going to be our CloudFront CDN. This CDN will interact with Amazon Cognito, which stores our user pools. So we can enable authentication and authorization at the CloudFront layer, as well as our API gateway, so that we know any users accessing this system are authorized and authenticated. The CloudFront will reach out to our S3 bucket and pull down the latest content of our interface. And our interface will give us configuration for interacting with our API. That interaction will occur through our API gateway, which will configure to proxy our traffic down to our Lambda functions and rate limit if we're getting too many requests. So then we can have one or many Lambda functions that define our API, however many we need to do so. And in this scenario that we're describing, one of these Lambda functions that will be for getting data, and for the scenario that we're describing, we'll have one Lambda function that is for querying data from our database that might generate a report in this scenario. This generate report Lambda function is going to take our requests that we do with whatever values we might want to be generating on, and it will create a JSON object that gets published to an SQS queue, a simple queue service. That way we can ensure first in, first out order from any number of users. And if we get an influx of traffic, we'll be able to handle that across our database. And this SQS then, once it's published to our queue service, our Aurora database will be listening for that queue and it'll take that query as they come. That query will run, it'll return a result, and that result will then be published to an SNS, which is our notification service. And we can set up our SNS to then be connected with either an email provider or an SMS to send a text message back to our client when that result is ready. So now we've transitioned from EC2 all the way to a fully serverless AWS architecture with each step and the trade-offs outlined. And in this architecture, we now have a scalable, cost-effective, and resilient infrastructure built out. So now that you have a decent understanding of AWS basics and the common services, next up we're going to show you how to deploy them using infrastructure as code, and more specifically, we're going to use Terraform to do that.
First, what is Terraform? So Terraform is an infrastructure as code language written by HashiCorp that's become a staple in the industry for a few key reasons. First, you can deploy and destroy any amount of resources with a single command. Second is that it's stateful, so we can configure our infrastructure as code, and then it checks the state to see what changes are required and makes those changes. Third is that it's version controlled, so we can track those changes across a team and in a single source of truth, which allows us to see when things change, who changed them, and if they broke, we can revert back. The last reason is that we can get an exact match on our environments. If we have a dev and a prod environment, we can configure modules that are reusable configurations and then pass in parameters such as our naming for dev and prod and ensure that we are using the exact same codes so that way our environments match one to one rather than in the past we had to rely on making those changes in both places and hope that we didn't make a mistake in one of them because then we have a misconfiguration and it makes it really difficult to track change and find bugs. Now in this walkthrough, we're going to go ahead and configure an Azure virtual machine from scratch and go through all of the steps that I would take to configure this with Terraform in a pre-existing project. Okay, so we are now in my home lab repository, and most of this won't be applicable here. This is how I provision my VMs for my home lab, but I want to add an Azure VM to connect into it. So to start, I'm going to come over to the provider here, and we're going to need to add into required providers now to use Azure RM. And I'm actually going to go check that to make sure I get the right one. So if you go to the Terraform registry and go to any Azure RM resource, you can actually check here. Yeah, and it's 4.16. So Copilot was way off. Be wary of that. 4.16. Okay, so there's our required providers, and now we actually need to configure our provider. So I actually copied this just out of another project. So we create the provider here with Azure RM. You have to have features, but we can just leave this blank. And then it's required to have a tenant ID and a subscription ID. Normally variables should be separate, but I like to include them in this part just for these type of variables so I know exactly where they're at. So if you're using this project, which source code will be linked below, make sure that you change out this tenant ID and the subscription ID from Azure. Next thing on the list, I'm going to create this as a module so that it's reusable and it's also split out to make my organization better. So under Terraform, I'm going to do modules slash Azure. Oh, I actually have modules already. Do modules slash Azure VM, and then I'll do a main.tf to start. So now on the Azure RM registry, here's a virtual machine. And to start, I am just going to copy out this, which is the example, and then we'll go through kind of how I would make changes here. Let's come back to my code, going to paste this in, and right from the top, so I'm going to want a prefix, but we're going to break that out. I'll leave that for now. Actually, I'm going to remove it so that we know that we get the errors here. I'm going to just make that var prefix. I'm going to make this prefix home lab as a variable passed in. I want this in West US. We have a virtual network we're going to create, and this will just be var prefix network. It's going to use the CIDR. Yeah, all of that looks good. And then we'll fix var prefix. Moving down, here's our internal subnet. So that's just using the resource group in the VNet. That's totally fine. Then we create a network interface. So this is what our virtual machine is going to use as the NIC. Prefix NIC will be perfect. Actually, I want to add -VM NIC just so I know in case I create any other. Test configuration 1. Let's change that to be our prefix. Yeah, that's perfect. Now we'll move down to the virtual machine part. So we're going to do var prefix again, -VM. And in case you're wondering what this does, so I'm going to pass in prefix and then it's just going to interpolate the string. So if I put in the prefix home lab, it'll do home lab -VM or home lab -VM IP. So that way we have one place that we pass that in and it configures for all of this. And that way, if I want to spin up a VM for a different project, I can put in a different name there. Okay, so these two comments, I want this to be totally ephemeral. So anytime I do Terraform destroy, I want everything removed. I'm doing it this way because I want to be able to destroy it when I'm not using it and just spin it back up without ever even thinking. I'm actually going to make this, so this will be var.computer name. Yeah, I'm going to make all of these variables. Okay, and then disable password. I might end up changing that, but I'll leave it for now. Root tags. equals var.tags. Okay, so now let's go ahead and define these resources that are missing. So first, I'm going to make a var.tf here. This is defined as a reusable module. If you're not familiar with these, basically, this is meant to be, we could put it in a registry and use it in all of our different projects. So we create this to be, think about this like a function if you're new to Terraform. It's like a big function that we pass in a bunch of parameters to, and then it does what we need. And so we just define that function. Now we're going to call that function from our main file. So I open up our main. Let's go down to the bottom. I'm going to call module here instead of resource, and it's going to prompt me. So module name, and then the source here. So it'll just be going into the modules directory locally. You can also make this a reference to a registry if you want. Our prefix, I'm going to name this home lab. Computer name is going to be home, actually K3S agent 2. I'm going to make that a variable now that I say that. I think these three should be variables. And then tags is going to be a locals block. So I'll do local.tags. And I'll fix that in a second. I'm going to do the variables first. Okay, so I'm going to go ahead back to my modules and just copy out these three values. Go into, I don't even have a var.tf here yet. That's how small this project is. So there's my var.tf. I'm going to define these three. And then now that we're in the outside directory, since this is just for the project, I'll define the defaults here. Okay, so I actually opted to not have default values on these. I put them inside my Terraform.tf This is where I configure what these values should be. So inside of that file, I basically have admin password equals and then what I set my password to be. But I have it in my git ignore. I included that file for this project. So I have some sensitive data in there that's not being exposed. So I'm not going to show you that file, but this is what it would look like. And then this format's a little messed up, so I'm going to go back to my terminal. Just from here, do Terraform format, and there we go. Now let's come back to our main.tf, and we need to define our tags now. So if I come into locals.tf, this is where we can kind of interpolate those values, and it gets, we can kind of make changes. It won't really be the best use case here, but it'll at least give you an example of what this would look like. So I'm going to do tags equals environment home lab, and then let's do created on equals timestamp. Okay, so this is a good one. I like to put created on all my resources so I know the exact time that they were created and how long they've been there. The benefit of this locals block is that now it acts like a variable, but instead of being a variable that's passed into the Terraform module, it happens at runtime. So this way we can do things like created on. I also, if I have that prefix from here, I could create a locals prefix from multiple different things. So if I wanted to create a prefix from dev dash region, I could take two variables and then create a new one from the two variables as a local, and then Terraform plan. Okay, so we were running into a problem, so I'm going to actually take this time to show you guys how to deal with this. So it's trying to refresh state. I've been having problems with my Proxmox provider, sometimes not connecting, and I'm just going to delete my VMs because I don't necessarily need them, but I need to delete them on Proxmox manually, and then I also need to get rid of them from the state so that it's not in there. So what I'm going to do down here, if I do Terraform state list, this will show my state, and now I can remove these manually. So this is, make sure you're only doing this if you know why you're doing it and what you're doing. But this is how we would modify the state directly. So I do Terraform state remove, and then I'm going to put these inside of single quotes for the ones that have quotes inside of them. And I can just put them all right on one line. So go ahead and do this. And then I'll remove that. And now I'm going to delete them from Proxmox manually. Okay, and now I commented them out from here, so they're not going to bother us. So now we're just down to our Azure VM. So then if I come back, let's do a new Terraform plan. Okay, plan succeeded. So we're going to go through this quickly, just make sure everything looks good. Let's get rid of that. And then let's go back. So that'll be no longer in here. So we're going to create a network interface, and it's in West US, resource group, home lab. All the rest I don't really care about, so it looks good. Resource group, West US 2, home lab. Going to create a subnet with the address prefix here. All of that looks good, has home labs here, and then standard DS1 VM. So that all looks good to me. Now I'm going to do a Terraform apply. So the apply just finished. Let's go over to Azure now and check our resources. Come in here and refresh. Here's our home lab resource group. Did that say West US? Well, I know two. Okay. Home lab. And then inside of here, so we have our virtual network, our virtual machine, our home lab NIC, and our virtual disk. Let's open this up. So this looks good, but that was first step. I like to get things built and then iteratively improve it. So now let's go back and make more modifications as we need. So I'm going to go ahead and just read through these, and then I'll come back with the ones that I know that I want to add or remove to customize this. Okay, so I'm going to configure an SSH block. So it looks like it takes in a key data block, which in this one, it's a file. And then it also takes in the path, which is here. And that looks like it stays the same. So what I'd like to do, I want to see if I can use my GitHub key. It's not going to make a difference, but I want to try it out. So I don't know if you know this, but if you go to your github.com and then your username and then .keys, you can get access to your public SSH keys here. So I want to see if I can just put in a URL for this. Okay, so let's go back. I'm going to come into our module here and down to our virtual machine. Let's do it down here towards the bottom, give us some space. Okay, so it looks like I was missing this block here, that's why. So let's come back. This should be inside of an OS block config. Tab that over, and that should be what we need. So now this is referencing the key data, which is the public URL. We're not going to disable password authentication yet. Like I said earlier, I probably will do this once I'm done here, but let's get it set up and it'll dynamically create the path for my username. So let's go ahead and do Terraform plan again. So it wants to change tags. This is because it's dynamically getting those tags at runtime. So I'm going to come in here and say, ignore, sorry, I need to do life cycle. So you can do a life cycle block. And then ignore changes. I'm going to take all of those out because I don't know if I need them or not, and I'm just going to do tags. So now what this is doing is saying that if tags has any changes, don't make a modification to the resource and let them be. That's also important. The reason why that happened is because the created on was changing. So it wants to do the created on as the new timestamp, which is say 10 minutes later. We want that created on to be the date that I started this. And then one other thing I want to do before we actually set this is now I'm going to set an enable block. So this is where we can use count. You can create resources with a count or for each. Those are the two types of basically loops in Terraform. Count is just make multiples of this. But the kind of hacky way, it's not necessarily recommended, but most people will use it, is to use count and then set it as a binary 0 or 1 or true or false. I'm going to define count here. And then I'm going to actually come into my variables up top. I want this to be right near the top so I can find it easily. Variable enable VM. And so we'll enable VM creation here, and we'll set that to true. So this will be var.enable VM. This is a conditional statement. So if var.vm is true, it will use the first value, which is 1. And if it's false, it will use 0. I'm going to go ahead and copy this to all of my resources now because I don't want this virtual machine or the network interface or any of those resources sitting around if I'm not using them. So now what this does is it changes how I reference this because this is going to be a list instead of a single resource. So I'm going to actually just do Terraform validate here, and you'll see missing instance key because it wants a 0 now. So everywhere that I have this value, I'll go ahead and do Control D so I can get a cursor at all of them, and then hit 0 there. And our validation just worked. So now we're in the clear. I'm going to go ahead and do a Terraform apply here and see what we get. So this is showing a bunch of changes. It's just because we changed this now to be a count. So it just has zeros here. So everything actually looks good. So for some reason, it's not adding my SSH key. So this will actually be a perfect example of how to use it now. I'm going to come back to my main.tf in the root, and there's this value now we have to add. Let's add it up here, enable VM, and I'm going to set that to true. And then we will actually set it to false. Go ahead and do our apply now, and this should delete everything. So this way, I don't have to comment code out. And let's actually set this to a variable. It's the way it should be done. Now come into my var.tf and let's add it all the way up top. So now if I'm not going to be using this virtual machine, all I have to do is go into my terraform.tf vars, set this value to false to override it, and then I'm good to go. I can destroy it. When I come back later, I can turn it on. And that's the benefit of using Terraform with cloud providers. Okay, our apply just worked. Everything is destroyed. Let's go show that quickly. So I come back to resource groups, hit refresh, nothing is there. Let's go ahead and spin these back up. So I'll run Terraform apply again, hoping to see that SSH change here. Here's our OS profile config for Linux, and it looks like it's going to use that key data. I don't know if that's going to work. I haven't done it that way before, but I'm hoping that's the case. And so we're going to press yes. So it did fail. I could, if I wanted to, just so you guys know, there is a way that you can use a curl block within Terraform as a provisioner. So I could curl these keys and then pass it in. That would be a lot of hacky stuff. So I'm not going to do that. I'm just going to do a file block. I'll make that change and then run it again. And there we go. It just finished. So if I come into Home Lab, press refresh, here's all of our resources, Home Lab VM, our virtual network, and the other resources. So now we can build all of our infrastructure with just a single true false value.
Now, quick jump here. This is going to be a different project, but I'm going to show you how to use Terraform now to deploy inside of a CI/CD pipeline so that you can automate your builds. Okay, so to start us off, here is my VS Code. And what you'll see, this is a project that I actually got pulled into. I added a couple files. We have our QSD PV Lambda, the SNS SQS, and then PDF PV ECS. So they just need a few things added to their infrastructure. And so I have scoped permissions down to what I'm able to build and not everything. So what that means is because we're running this through Bitbucket, the only way to see what actually happens is inside of the Bitbucket pipelines. But I want to make sure that these changes are safe before I push them just to get that developer feedback earlier in the process. So what I can do here is I can actually run a Terraform plan. I'm going to point to the var file for the pre-developed environment because that's how they're referencing here. And then what you'll see here is I just target each of these. So I ran target module.qsd pc lambda preamble. So that'll be in here right here. And I'm targeting all the resources that I want to hit. And then what you'll see is it's just fresh. If I just ran this by itself, I can actually just scroll up and show you. What you'll see is I don't have access to all these resources like I should it. So I can't run this otherwise. It just plans and it fails because I don't have the permissions. So now that I've added these resources and I've run this plan, and I'll show you here, I'm on a different branch from the pre-develop. So I have this echo image gen, and it's based off of pre-develop. So I've already pushed this. So if I come into my Bitbucket now, I will go over to pull request, and I've already opened this up. So let's go check these files changed. So we have data.tf. No. So what we're looking for here, I just want to make sure that I didn't break any of their pre-existing infrastructure. It really should be all fresh changes. I shouldn't be changing anything they have. So I added in these two data blocks. I wanted to be able to reference the account number and the AWS region through a data block so that way because each of their environments is in its own account. So I wanted to be able to just pull out the account number from there. And if they change region, it wanted to do that automatically rather than having it hard-coded. Next up, we add in our ECS cluster. So they wanted an ECS cluster and two ECS task definitions. So that's what you'll see here. Again, totally fresh. There's nothing getting deleted or modified here, so that's fine. We have our SNS SQS. This is just a couple different queues that are going to be... These are just a couple different queues. They're running a pub sub model to make it event driven. So these are just going to kick off those ECS jobs and lambdas as needed. And then lastly, we have our Lambda function here. So again, nothing crazy. It's a Node.js 20x running. And I just upload a dummy.js file. So this is a zip file that it just contains index hello world for the handler. And we're going to manage that elsewhere. So they'll have a Git action so they'll have a pipeline that can just deploy to that Lambda, and we'll just build the infrastructure with Terraform here. So now that that's done, how does this actually deploy? So we haven't actually seen any pipelines run here yet because we haven't merged it, which you can set up a speculative merge as well. They haven't done that yet, but that is something I'd recommend as you get to a more advanced state. But if I open up our repository here, I'm going to open up our bitbucket pipelines.yaml. And what we'll see here, this is a pretty large file. This is where we actually define what we want to do every time a merge happens. So I'm actually going to skip these steps first and show you what the triggers are. So if I come down to pipelines, branches, and then you'll see here pre-develop. So this is the branch that we're going to be merging into from our Echo image gen. And it basically says every time that branch gets merged into or there's any change there, run all of these steps. So we'll do security check, which if we scroll up here, should be towards the top. So here's our step 1, and this is going to do init and validate. Step 2 is going to be pre-dev plan. So we're going to run Terraform plan, make sure there's no errors. If so, we obviously don't want to be applying. And then if that passes, run Terraform apply. So this is where our infrastructure actually will be changed. So we set all of our values, run init, and then we do a Terraform plan and apply based off of that plan file. And so those are all the steps we're going to be running. If I scroll down here again now, what you'll see, it's commented out because they're only in pre-dev at the moment. But what this eventually looks like is that we have one Bitbucket pipelines, and we set up each branch to have its own steps. So these steps are going to match in this case, but you can have differences. But we set everything as variables, so our environment variables for our access keys will be set here, and it'll know which one to reference at the time. And then we run all of these steps, and now it's all from one place. So if I merge from pre-develop into develop, run this. If I merge from develop into QA, run it again for that one. And the variables will be what change, what environment we're pointing to, as well as our environments up here. So if I move here now, the way this works is that we just have environments set up for each environment developed through to prod, and each one has its own TF backend and then its own TF var. So this is all the variables relative to our pre-developed branch, and those will be different for each branch that we're in. And so now I'm not ready to merge my change yet. So now let's open up the most recent one that's been run, and we'll see the status is paused, so we'll look into that. So we did security scan here, and then we ran Terraform init and validate. We do our plan. All of these are good, so we move on to the apply. And here we go. It does Terraform apply with auto approve set. And what you can see here, the Terraform plan is setting out the file. If I can actually extend this. So what we'll see here, the Terraform plan is setting an out file for plain file / and then the branch name .plan. And then the Terraform apply is running auto approve, and it's taking in from the plan file. So this runs, everything looks good. Here's all of our changes, apply complete. And then this one's actually paused. I don't love the way that this is set up, that they have it waiting for Terraform destroy, because that should really be a flag that should be set in, so it doesn't just wait every time they run. Okay, so here's all the pieces we're going to go through. So most of this you'll see is networking-wise. We have VPC, subnets, endpoints, internet gateway. I'm going to break all that stuff down first, and then I have a few other key services. So I have over here RDS, DynamoDB. This is an S3 bucket, and then we have EC2. So I'll show you where those things would actually fit inside of your network. I know sometimes it can be confusing, like, is it in my subnet? Is it not? Is it connected through an endpoint? So I'm going to break down those services, how they work in with your network. So to start us off here, inside we have our AWS cloud, and then inside of that we have a VPC. So VPC is a virtual private cloud. You'll have one by default, and you can create more from in there. Basically, this will have a certain CIDR block. So a CIDR block in this case is 10.0.0.0/16. The CIDR block tells us that we have, out of 32, we have 16, I guess 2 to the 16th of IPs available. So what this means, each of these numbers is called an octet. So we have 8 options here, 8 here, 8 here, and 8 here. So this means that the last 2 can change. The reason this is the case, if you know binary, each of these numbers from 0 to 255 can be broken into binary. So we're not going to change the first 6 of these, but they're actually broken down into what the binary value is. But then we can change the last 16 binary values out of this 32-digit binary, which gets broken into this octet, or 4 octets rather. So in this case, our VPC will have any IPs from 10.0, that'll be static, and then this third 0 and the fourth 0 can be anything from 0 all the way up to 255. So that gives us 256 times 256 IPs, which would be 65,000. So pretty large VPC that we have here. And then inside of that, we break down our VPCs with subnets. So subnets are like a logical isolation to our resources. So you'll want to break things down based off of how they interact with other resources, putting similar type of interaction based resources in the same subnet. So in this case, we have a private and we have a public subnet. And there's not much, like everything can communicate if you add in the routes and it's all inside the same VPC, but it gives you more ability to restrict that traffic as needed. So we have a private subnet and a public subnet. Now, the only difference here is a public subnet will have an internet gateway. So our internet gateway, or we'll have access to it rather. So we'll put an internet gateway inside of our VPC, and then our subnets are allowed to talk to it. So this is basically a way to connect to the internet. So this way, private subnet cannot reach the internet. Public subnet can, because it has access to both go inbound and outbound. And that's also ingress is like I am going into the public subnet. If I have an instance in there that's hosting a web server and I'm the user of that site, I am ingressing to it, versus if I log into that server and I make a request to download some package from the internet, that is egress out of the subnet. So from there, one of those situations, if you're, say, trying to download some packages to update your EC2 instance, but it's in a private subnet, sometimes you do want internet access, but you only want egress. So in that case, we will use a NAT gateway. So we'll add in a NAT gateway here, and this acts very similar to the private sub, or to the internet gateway rather, but this one is only outbound. So now our private subnets have access to go through the NAT gateway out to the internet and pull down whatever data they need, but it's only going out. So I could not have any possible way to connect into an EC2 instance or whatever it is that you're running in that private subnet if it only has NAT gateway access. If you have a route that goes to your internet gateway, then it would be public. So now what I just said there, route, just by adding these to the VPC does not inherently give us access, because I add the internet gateway, I add the NAT gateway, but how do I know which subnet can talk to them? So that's where route tables come in. So our route table is where we define what can access what. Think about it like it's a GPS for your communication inside. So I'm actually going to open up the console here. So if I come over here to VPC, and what we'll see here, we do have a VPC that's available. And you'll see it was created by Control Tower, so it's just our default. Here's our CIDR, so this has 10.3 static, the rest are available. So we're actually going to go into our subnets here, and you'll see here we have private and public, and I'm going to just open up this public subnet. And now inside of this public subnet, we'll have a route table associated here. So in this one, we have every single subnet has a route table that is unique to it. And here's our route table. So all traffic that is 10.3 prefix, anything 10.3, 0 to 255, will go to local. So that means keep it inside of our subnet. Anything past that is 00, this is basically any IP address in the world, send it out to our internet gateway. So basically, if our DNS resolves or if we use an endpoint with an IP and it comes back and it's not in 10.3, then just send it to the internet and see if it exists there. And then we also, we'll get to this later, we do have a route that goes to a VPC endpoint. So think about the routes again just as a map or a GPS to when I give an IP address, where do I go look for that IP address? Okay, so next up, we're going to talk about our DNS resolution. So if we have our DNS resolution, there are two types of DNS resolution, and you're probably familiar with Route 53 if you're using Amazon. So with Route 53, we set up our domain to be accessing it. You set up the name servers, and then from there, you can configure it to what traffic you want to point to where. So like we might have a CNAME alias that when you go to www.google.com, it sends you to the IP address or the load balancer rather that hosts Google. So with this, that would be public resolution. And this is a whole nother video I could do. Let me know in the comments if you'd be interested in that. This way is how our actual domain resolution happens on a global scale with these public name servers. But you can also have private. So with private resolvers, we can actually add our own resolver within our private network. And then from there, this would be like if you have a VPN, so your connection goes from your local laptop or your gateway, your modem at your house. it flows as a proxy through your VPN within this network now, and then goes to where it needs to go. That's how VPNs are structured. You might have a site, if you work at a large corporate company right now that has a VPN, that you go to the site and it loads when you're on the VPN, but then you try to connect and it just gets a timeout or it doesn't exist when you're not on it. That's because it doesn't know how to resolve the DNS because it's private. So within this, we have our VPN, and this can now communicate up to our DNS resolution, come back and say, hey, the site you're looking for is actually at 10.0.1.1, go there. And then that's how your connection goes to your EC2 instance that's a website that's hosted right next to it. So that's the flow of the traffic here. And we can only make that available for private resolvers from inside of our network. The next thing I want to talk about is availability zones and regions. So you've probably seen you have different regions when you come up here to the top where you can select US East 1 to US West, whatever it might be. Within that, you also have availability zones. So our availability zones are inside of those regions, and you'll usually see US East 1 to, US East 1A, 1B, 1C, etc. So these are different kind of fault zones inside of there. So you can think about it if you like plop different data centers on a map. These ones are in Virginia, in North Virginia, because they're in US East 1. But we might have 3 different addresses that are running data centers where your code is actually being run. And so if one data center had an earthquake and it goes down, our data center in US East 1B might still be working. And that's how we can say make a site highly distributed by, if this is our web app, we can host an instance here, host an instance over here, and then have a load balancer that connects the two. And so this traffic would flow from load balancer that can be in each of these public subnets, and this will then balance out that traffic so that if private subnet 1 is just deleted, we'll get rid of this, then it'll automatically flow the traffic down here to our web app in private subnet 2. Okay, so here's our clean diagram again. I went ahead and removed everything. I left the internet gateway and the NAT gateway. I don't have any arrows pointing to it. I don't have the route tables, any of that, just for simplicity. Just want to go through now how our services might work together. So these are the core services we're going to go through. We have Lambda function, EC2, S3 bucket, Dynamo, RDS, and then just general VPC endpoints. So first, EC2, this is always going to be in a subnet. So you will need to put it somewhere. You'll have to have a VPC available. You can throw it in a public subnet, and then I could SSH into my public subnet if I wanted, or I could throw it in a private subnet if it's just running some job that doesn't really matter and it has to connect to some other stuff. If you need to make it secure, but you also need to SSH into it, that's where you might hear jump box. So I can make one in a private subnet and then go ahead and make a jump box in a public subnet. This is just another EC2 instance, but this would allow SSH traffic into my public subnet, and then the traffic from there, because it's now in my network, can flow to the private subnet. And real quickly, the way that we would do that is with security groups. So I'll just show you this in the portal. Security groups are another layer of protection. You'll see this is the default one. It comes with every VPC. So this is just allow everything. These allow us that ingress or inbound and outbound or egress traffic control. So what you'll see here, we have everything everywhere. You can do all types of traffic on all protocols, on all port ranges. It's just doors are wide open. And same thing on outbound. Generally, doing that on outbound is less of a problem. Some large corporate companies won't let you do that, but inbound rules never do this in any kind of production state. So what I might do is go in here. I could get rid of this rule. I'm not going to for this case, but I'll just add a rule. So I can do custom TCP. So let's do HTTPS. So if I'm hosting a website, I only want to allow HTTPS on port 443 to come in. And then I can go ahead and select my CIDR. So for this one, I want anyone in the world to access my website because I'm trying to grow the user base. So I'm just going to do 00 all the way. That means any IP in the world. So now we've at least limited this, if I were to delete this rule, to where instead of you being able to SSH into my server, you can only access it over HTTPS. And we can do all kinds of things from here where I could say whatever port I want from 0 to like 65,000 something. You can do IPv4, you could do IPv6. I could click my IP. So if I wanted to SSH, clicking my IP would be best. I'm not going to do that because I don't want to show it. but that would just limit to my current IP that I'm accessing this from. And then at least that's better. You don't want to keep that in long term because your IP probably rotates, but that's a good way to do it if you're just quickly making a jump box. But so moving back here, we're going to say that we have our EC2 now in our private subnet, and that's going to be hosting some API server, we'll say. Now, let's go ahead and build out a RDS database. We want this to be distributed across our two private subnets. So RDS is like EC2, it needs a subnet. So we will build this both in our private subnets. Make sure you always do that. Don't have internet traffic to your RDS. Use some other way to access it from the network level, whether that's your jump box or ideally you're using some endpoints or your EC2 is already in there, that sort of thing. So this way we can distribute our RDS between our two private subnets and it's fully private from the internet. These are actually inside of our VPC. Now, if we want to talk about, let's say, an S3 bucket, you cannot put an S3 bucket inside of a VPC. S3 buckets don't allow that, but what they do allow is VPC endpoints. So what I can do is go ahead and add a VPC endpoint up here for our S3. And we'll go ahead. Now, by adding this private endpoint here, this actually allows us, so I could then send traffic through the private gateway and it goes to my S3 bucket that way. So this will allow me, when I reach out to aws.s3, whatever the URL is, instead of going out through the internet, you can actually picture it like this. It would go down to our internet gateway and then go out to the internet and then loop all the way back around to our S3 bucket, get the response, send it back through that same path and into our EC2. Now, we're waiting for the time it takes to do that, and we're also paying for any data transfer costs that occur in that situation. Now, the better way to do that is we add in this private gateway. This is where that public-private DNS resolution is. The private will take priority, so when we go to s3.aws, whatever our URL is, it now hits this private interface or gateway that's inside of our VPC. It's a big jump going out to the internet rather than just going through a gateway that brings you direct access to it. And there are some cost benefits to it as well as security. Now I'll go ahead and add DynamoDB in as well. Dynamo is the exact same thing as S3 in that sense. We add in a gateway that allows access to our instance. So, or rather to the Dynamo service. So we only add one-to-one. It's not like you have to add a new gateway for every single S3 bucket. You're basically just changing where that traffic gets routed from public to private for S3 and DynamoDB, whereas the RDS are actual instances being run in the cluster. Now, something else we have is Lambda function, and this is the most unique of them all. Lambda functions can do both. When you build a Lambda function by default, it is run on the AWS network. I don't know the term for it. Azure has Azure Backbone. AWS, it's just the AWS network that is their network that is managed, where it's not in our own VPC. So the Lambda function here will run, we can connect to our S3 bucket over the internet. We can connect to our DynamoDB bucket or DynamoDB table. Whatever we want to do, that all can happen. That's fine. The way that we want to make that traffic private, though, we can actually, unlike S3 and Dynamo, we can put this inside of a private subnet. So Lambda is might be the only that you can do both. You can have it outside on the AWS network or inside your own subnet. And this is usually like if you have an API that is connecting into your RDS, put it inside your private subnet, and then it connects to your RDS and it's right there. Again, routes, whatever you need. Now, again, that's assuming all the other stuff, such as the security groups allow it. You have any NACLs in place, you have a firewall, all that stuff. Assuming that's allowed, we can then put our Lambda function inside of here. And then if your Lambda has to pull data and put it into S3, we can now access that S3 endpoint from inside of our VPC rather than going through the internet again.
So let's kick this off. We're going to go through the core concepts of Docker and Kubernetes. We're going to go through some hands-on building of Docker containers, Docker images, and how we can deploy them on Kubernetes after. Start things off here with this diagram at the top. So a lot of people think that like you replace Docker with Kubernetes, one or the other. Which one is it? It's a verse conversation, but it's not. Docker creates images, which you can create containers from, and Kubernetes orchestrates those containers. So Docker is one of the big container runtimes, but there are many others like Containerd and Podman. And there's other replacements to Kubernetes, but Kubernetes is really the winner right now. So containers solve these problems. It creates a consistent environment from development to production, and it allows us to easily scale deployments because once we build a container, we can spin it up as many times as we want. So now, containers versus VMs. What is the difference? This is really important to understand as it is, but it's also a really common interview question that I've had. So make sure you know this. Containers are lightweight, they can start up in seconds, and the thing is they share the operating system kernel here. They're less resources and they're great for microservices, but they don't have the isolation that VMs offer. So if we scroll down here, this diagram shows a virtual machine versus a container. So in a virtual machine, we have the infrastructure, which would be our actual like server rack, the metal that it's running on. And then we have our hypervisor. So this is what breaks that one server into multiple, and we can virtualize it is with the hypervisor. So this would be a hypervisor that has 3 different machines on it, where there's 3 operating systems, 3 dependency libraries, and then 3 apps, all at this layer. Whereas if we look over at the containers, so we have our infrastructure, which is the metal, we have our operating system, and then on top of that operating system, we have a container engine, and then our libraries and our apps are in that container engine. So you'll see there's not 3 operating systems. They all share the operating system or the kernel. So if you get asked this, the key thing you want to say is that containers share the kernel, virtual machines have their own kernel. So moving on down here, that kind of gives the basics of why containers, etc. So a few key terms I'll define before we move forward. Docker image is like our blueprint. We define what our image that we'll build from should be. And then a container is the running instance of a image. And we'll use a Docker file here in a second to create those images. So before we go ahead and pull this Nginx image, I'm going to show you guys how to get this stuff installed. So I like Rancher Desktop. You can do this whatever OS you're on. Look up Rancher Desktop, come down here and open up the Get Started with Rancher. And you'll see here, it's going to install these things. Helm is great. kubectl we're going to use in this video, and the other stuff will apply. It's different container engines and Docker Compose, but I'll let you read into them yourself. So to install this, we're going to come over to the releases page and then just download whatever version you'll be using. So I'm on a Mac M1 chip, so that would be an AArch64. Just find whatever one you need and install it. The install's very basic, and we'll move forward from there. So once you get it installed, I'm going to open up my Rancher Desktop now. And over here, you'll see immediately it's going to start virtual machine. So this is actually a hypervisor like we were just talking. So this is going to create a virtual machine inside of my Mac that I'm currently using. While that's starting, we'll go through here. So we have general, nothing really in here. Containers, this is going to show what containers are running once this loads. Port forwarding, this will be if we have any services available. And then images will be the images that are built and available within our local registry. Lastly, come down to preferences, and you're going to want to go through to Kubernetes, press enable Kubernetes, and you can change it to the latest stable version. And then go ahead, leave the port the same and press apply. And it'll restart that creating VM once you do that. But that way we'll have Kubernetes when we're ready. Other thing, container engine, we have Docker D. You can change this to Containerd because that's generally what's used with Kubernetes, but they function basically the same. It's abstracted so well that you won't even notice the difference. So it doesn't really matter what you use. Docker is the big one, so I'm going to stick with it. And then in virtual machine, you can change up that hypervisor that we're configuring with the virtual machine. I can bump up the memory and the CPUs of my virtual machine if I'd like to. Just be wary that that's going to slow down your actual machine because it's eating up the resources. So I'm going to keep mine here for now, but if you guys have larger machines with more memory and CPU available, go ahead and bump that up. Now that this is loaded, you'll see in here we have some images built. I'll get into that later. So go ahead and open up your terminal. I'm not sure if Rancher installs Docker for you, but if not, you can just do brew install Docker like this or whatever package manager you use. You can also use Podman for this video. You'll just replace Docker with Podman everywhere you see it, and it'll be the same outcome. Okay, so to get us started, now that we have Rancher installed, we're going to go ahead and pull our first image. So I'm going to do Docker pull nginx from here, and I'll go ahead and copy that to my terminal. And you'll see it's going to pull the default tag with latest. So if I go to Docker Hub, this is Docker's public registry of all of their kind of like certified images, or at least some of them they have certified and say that these are good. Always be careful pulling ones that are not like large images that have been verified, because I could go put an image on here with some sort of malware and tell you to pull it and run it, and now you're running malware on your computer. So especially be careful in production environments. But if I scroll down here, you'll see actually most pulled images. This nginx image has over a billion pulls, funny enough. So I'm going to open this up, and there are all kinds of tags in here, lots of information on it. We're using the latest, so it's actually up here, Docker pull nginx. It just pulls whatever tag has been most recently created. So here are all the options for tags. We're just going to pull the most recent. So now we see that's been pulled. Let's go ahead back to our commands, and we're going to run Docker run -d-p port 80 into port 80 nginx. So what does that mean? We are saying we want to run this on port 80 from our local host into the container's port 80, and it's going to be the nginx image. So we are creating a container instance from an image. So if I do Docker image ls, you'll see here all of our images that we have created, which I've already pulled this nginx, so it's been 2 months, but that's the one that's there. And then if I do Docker ps, we can now see our processes that are running. And here is our latest nginx, the command we used, how long ago it was created, etc. Okay, so now I'm going to do Docker ps again. Let's find that name. So this one's Naughty Bernal. It's automatically creates the names. There's some funny ones, but I'm going to do Docker kill and then kill that name. Now let's clear our screen and let's go back to our sites. So the next thing we're going to do, we're going to create a Docker file. So to start us up, I'm going to open up my directory here and go ahead to this Docker file. So this Docker file is going to be our baseline. We have an nginx repository, we have a Next.js repository here that we're going to be building, and we'll go through what the Docker file is doing. So the first line is going to be from in all Docker files. This is our base image. Think about it like the foundation, like what is our starting point to build on top of. So we grab our starting point, which in this case is node 18, and then we build on top of that. Next thing is going to be our work directory. So we're going to just set this to /app. Think about it like your home directory. When you open up your terminal, where do you start at? Where does everything go? That's going to be /app. Copy package.json. So this is going to copy everything into / that has package star.json. So that would be the package.json and package lock.json. Then we will install our dependencies, and then we copy everything over. So you'll see there's 2 copies. That's really important, and we'll get to that in a second. Next thing, this is something, it doesn't really change much in the container, but it's good for documenting it. We're going to expose port 3000, so that just tells what port is going to be used on this container. And then lastly, every Docker file should have a CMD line or command. This one will be npm start. So all of this is like packaging up layers. And then the final one is when we invoke this image that has been built, what command do we run? Let's go ahead and build our Docker file now, or our Docker image from our Docker file. So I'll do Docker build -t. I'll tag it as my image, and I'm going to do a period to say build here. And the other thing, I need -f for a file name. So this is going to be dockerfile.learn. If you don't put -f, it will automatically take in just Dockerfile with a capital D by default, but you can specify file names this way. So I'm going to go ahead and build that. Okay, so now while that's running, let's come back here And we'll talk about why there's two copy commands. So each of these, think about them as a layer. It's not always the case, but generally you can think that way. We're copying the package.json over, and then we run npm install, and then we copy everything. So anytime one of these layers changes, we need to run everything past that. So again, it's like we're building a cake where each layer stacks on one another, but it's dependent on the prior. So if we look at this, we have our base layer. This image layer 1 would be like our copy package JSON. Image layer 2 would be our dependency install. And then image layer 3 would be copy everything else. So the problem is if we reverse that now and we copy everything else first, and then we change, say we come into our app.tsx and we make a small change. Now, because that copy is up here actually, that means that this has now changed and we need to run this command, then this command, then this command. Whereas in this case, we only have copy after. So if I change our app.tsx, we can just run npm install and that's already been done and it hasn't changed. So now we just copy the files. So you want to order these. So you want to order your Docker file by the priority, basically, which you would derive from how frequently am I changing this and how long does it take. So we know npm install comes from the package.json. We change it infrequently and it takes a long time to install. Versus copy all of the files takes less than a second. So we're changing it frequently and it happens so quickly that if we put it towards the bottom, then we're not going to affect these two in our build. Let's come back to our terminal and we see this has been built. So there we go. If we do docker image ls, and here is our new my image has just been built. For some reason, it's showing 2 hours ago. Not sure what's going on with my timing here. I just did a restart, so maybe there's a problem there, but we can assume that was recent. Next up, let's come into a two-part build. So here we have a build stage and a production stage. So again, we have a from, we're going to pull from node this time, 18 Alpine, that's like the thin version, but we do as builder. So we're naming our stage. This is going to be very similar to the last one we just looked at, except this time we do npm run build rather than npm start. So we're creating an output file or output directory that can be used in another stage. So if we move down, we have nginx Alpine, and then copy from builder, so referencing up here, from the app/dist inside of this builder, we're going to now copy into our nginx directory. So we install our dependencies and then create a static output, and then we copy that static output. So what we did here, we're basically building this and then we're scrapping it when we're done, which means all of our dependencies are getting thrown away and we don't have to worry about the space they take up. A few other small things here. We're going to copy in our config file from our nginx, expose port 80, and then turn it on. So let's go ahead and build this one now. And this was meant to be my image prod, had a little typo there, but this built, you'll see how fast that built. I'll do docker image ls. And here is my image rod. Look at the size difference, 51.1 MB versus 1.37 gigabytes. So we threw away all the dependencies after we created the output file, and we just saved so much space. So that's why this is so important. We need these multi-stage deployments or multi-stage builds to be able to make lightweight containers that don't have to carry around all their dependencies if not required. Next up, I'm going to go ahead and run this. So I'm going to do docker run -d-p. I will do 3000 into 80. And I need my name, so that is going to be my image rod. Now I'll do docker ps. We should see that is now running. There we go. Let's go see if that's working. And there we go. My website is now running on my local host, and this is going into that container that is hosted on nginx. Okay, now we have got the basics of Docker. One quick thing I want to show you, there is a Docker cheat sheet. So I didn't tell you every single command that exists in Docker. There's tons of them. I wanted to show what's relevant and what needs to get you started. And then the other stuff you'll find when you need it. But there are two I wanted to shout out.
So you can reference this cheat sheet as you guys are using Docker and building out your first project. Two that are very helpful that I wish I knew earlier. Docker exec. So this is Docker exec -it, which means interactive terminal. You tell it what container and then sh to give it a shell. So you could also do PowerShell here, whatever kind of container you're running. This will get you, it's like SSHing into a machine. It gets you inside of the container. So then you can see, okay, what files are actually here, what logs are coming out, what processes are running. And then Docker logs, you can just output the log stream from the container. So these two are so good in debugging when you're building out containers initially. Just wanted to show them and have you guys reference this cheat sheet as you're pulling other stuff. Next up, let's go ahead and get into Kubernetes. So we just learned how to create containers off of images and provisioning those images from the Docker file. Now, how do we manage containers? That's where Kubernetes comes in. So Kubernetes is a container orchestration platform. So we're orchestrating containers. So think about how we can spin them up and spin them down and manage those containers, set up the services and the networking required to use them effectively at scale. So the core concepts, we have pods, we have services, and we have deployments. Pods are the smallest unit and they contain one or more containers. So generally when you're starting out, you can look at this as being a one-to-one mapping from container to pod, but that is not always the case. There are certain situations such as, say, if you're making a database, you might have an init pod, which will, when you go to run your database, it'll run an init that can do some pre-processing or pre-scripting to set up the environment for your database, and then the database container runs. Or if you have, say, a service mesh, which we won't get into in this video, but that basically acts as a proxy. So you create what's called a sidecar container to sit next to your container that is hosting, say, your web app, and the traffic is proxied through that container. So in that case, there would be 2 containers per pod. But the pod is just, you can think about it as a container for the purposes of this introduction and for a while getting started until you have to start using them otherwise. Services, so this is just how we expose our pods to be available within the network. So whether that is external to the cluster or internal to the cluster, services are how we do that. And there are different types of services based off of that internal versus external. Lastly, we have deployments. So deployments are the declarative infrastructure for how we manage our pods. So we scroll down here, we have a basic Kubernetes YAML file. We have the API version, which is the API of Kubernetes that we're using. So we have deployment here. That could be service, that could be pod, etc., or any type of custom resource definition, which will be covered later. Moving down, we have replicas here. So this is saying I want 3 instances of my image to be built. We label it with Nginx. We'll ignore these for now. The container section now. So we want our container to be named Nginx. We want the image to be Nginx latest. And ports is container port 80. So that's what port are we accessing on. So you can map this to what we just did in Docker, where we did Docker pull Nginx and then Docker run -p port 80. That's what we're configuring here in the YAML. So let's go ahead to our rancher and we will get started with Kubernetes. So if you selected to enable it before, you'll now see cluster dashboard. Go ahead and open this up. And inside of here, we can see it's a dashboard to interact with our Kubernetes cluster. You can use the CLI to do everything. This is good for when you're learning to get a visual representation of how the hierarchy of these different resources act. But I'd be hesitant to making change in here just because I think the CLI gives you a better understanding of what's happening when you do it and repeat those steps. But coming in here just to view your deployments and view your nodes and your resources is helpful to get that really, really high level when you're starting. So I'll run through quickly. We have a cluster. Inside of that, we have a namespace, or we have namespaces, which are defined here. These are just the default ones. We can create namespaces as well. Then we have nodes. So inside of here, we have just one node, and the node, think about that as the virtual machine or the actual machine that this is running on. So if we ran this on AWS and we had it across 3 EC2 instances, we would have 3 nodes. And then on each node, we can spin up new instances. So Rancher has deployed K3s for us. You'll usually see Kubernetes talked to as K8s.
K8s is using a couple different things. It's a more heavyweight, but also more reliable system. It uses etcd as the database, which you can cluster and have highly available. Whereas my K3s cluster here is just running SQLite to store the state. So it's a little less dependable, but it's great for things like this where you're working and learning Kubernetes and just need something really small and lightweight. Next up, let's go ahead and get into our cluster. So I'm going to copy this out actually and go ahead into our terminal. Okay, so here is a new file that I just created, and I copied that stuff into it, and this will just create Nginx. So let's change this. I had it as my first deployment. I'm just going to make it deployment.yaml. The naming doesn't matter. It's just how you reference it from the command line. So to start things off with our Kubernetes CLI, we're going to come in and we're going to do k-get nodes-a, and you should see this. If you have a problem seeing this, or if there's like an HTTP error, you can look up your kube config. So you should see, I'm going to cat this. This is a sensitive file, but because this is on my local machine, I'm okay with showing it. I'll delete it after and make a change to it. But let's do cat:/.kube config. And you'll see here, this is how we actually connect. So it's my Rancher desktop cluster, my Rancher desktop context, and then we access it where we get authorization into our cluster with a client certificate, which is here. So this is the file that actually allows us to access it. You might have a problem in there if you've used Kubernetes before and you have a different one, but you'll have to change your Kubernetes cluster or your config to match to whatever your Rancher desktop has set up for you. And you can come into your Rancher desktop and actually copy that out if you need by going to cluster dashboard, and then right up here you can copy. Let's do k-get pods, and this is in default. So if we add -a, this will show everything. So here's all of our pods. We're going to do k-get ns. That'll show all of our namespaces, and then k-get services, and this will show all of our services. I'm going to do this in another namespace. So what I'm going to do is k create namespace, and we're going to call this demo. So now if I do k-get ns, we should have a demo namespace. Now namespaces are very important because they're the isolation layer within the cluster. So it's how we split things up inside of it. So we want to make a namespace for our apps, for our databases, etc. So now we're going to go ahead and create our first deployment. So if I come over to my VS Code here, I copied this from that site that I had set up. And for now, we're just going to pull in Nginx. So we want that Nginx with the 3 replicas like we went through before. Now, if I come over to my CLI, I'm going to do k apply -f, and then that'll be file name, and we'll put in the name of the file. And there we go, it created. So now if I do k-get pods-a again, you'll see this actually, it's creating right now in the default namespace. And I did not want to do that. So what I can do is k-get deployments. So I created a deployment that creates these pods. So in order to delete this, I want to delete the deployment. So I'll go ahead and do this, k delete deployment, and name it that. And now when I do -f deployment, and I can also add in -n for namespace demo. So now if I do this again, there will be inside of demo, now we have our deployment and it says 0 of 3 ready. So we just created this deployment and this manages our pods. So this is one of the fun things of Kubernetes because it's self-healing. So our deployment knows that we want 3 pods at all times and it's going to keep that. So let's do k-get pods-a. We'll see here, these 3 are running for 23 seconds. I'm going to just delete one. So I'll do k delete pod-n demo and then the name of the pod, and then do k-get pods-n demo. And now look at this, it's already creating because our deployment says we needed 3 and there was only 2 because I deleted 1. So that's how we can get into that self-healing state with our Kubernetes deployments, managing our pods. Okay, so now that we have our deployments managing our pods, we need a way to access our pods. So we can directly access the pods, but we can't expose them to the network like we want to. So we want to create a service. So I'm going to come into this deployment. I'm going to do 3 dashes because that signifies another Kubernetes resource is being created. And then I'm just going to ask Copilot, make me an externally available service. And I say externally available. The main thing there is that's going to make this into a load balancer now so that it's accessible from outside of the cluster. We could do a cluster IP, which would mean, like, say I had an application server that wanted to reach a database. I could make the database service cluster IP. So you can't access it if you're not in the cluster, but your application server can reach in there because it's already in the cluster. And now I'll come back to my terminal. I'm going to run that k apply again. And no changes to it. You'll see the deployment is unchanged. So since we configure it as code, it knows what it is versus what it's expected to be. And because it matches, it doesn't make changes. It's not going to make another one because that one already exists and it knows that's what we're looking for. But we did create our new service. So let's do k get service -n demo. And here we go. Our service has been created. And this isn't going to create an external IP because I haven't set it up yet with my Rancher. I already said that. But what we can do is open up our Rancher desktop and then come into port forwarding. And you'll see now this is available, but there's no local port. So we can forward it. And I'm just going to set this to 3000. So now if I open up localhost 3000, here we go. My web app is now available and it's running in a container on Kubernetes. So the next thing I want to show is how we can scale our deployments. So let's do k get deployments again, just to show where we're at. So we have the 5 of these. We're going to just look at the demo ones. Let's do -n demo. And now see how we say ready 3 out of 3. I'm going to scale this up to 5. So if I run k scale deployment, and then we can name it Nginx deployment, put in our namespace of demo, and I'm going to set replicas equal to 5. And now, k get deployment, 3 out of 5. So it's trying to make those 5. If I do k get pods -n demo, now we see 3 that are currently running and 2 are actively creating. So while that might not be the most useful because we just had to manually do it, it can be good if there's a rush of traffic coming in, you can do it. But it's great when you can set these things based off parameters and set auto scaling. So we can configure our deployment to say, if our server reaches 80% of the max CPU, then scale it up. So we could have anywhere from 1 pod all the way up to 1,000 pods. And as the CPU increment gets matched, we will scale it up. And then we use services to balance the traffic across those pods distributed. So that way we can keep that consistent traffic. And then if we reach under, say, 40%, we can scale down. And you can think about it like climbing a ladder. Like we climb up every time we get more traffic, or we climb back down every time our traffic goes under that threshold. So we run this again, you'll see now we have 5 pods here, and then we still have our service that is pointing to the deployment. But one of the problems here is, if you remember in our VS Code, we defined our replicas here. So if I do k apply again, it's going to change our deployment to be back to 5. And so the problem there is that now we have 2 sources of truth. We changed it manually, but we also have our code that runs it. So this is where I want to introduce Gitops.
Okay, so it started back in 2014 when Google created Kubernetes because they needed a way to run massive systems across multiple machines without all the manual work. So the goal was to automate and scale the infrastructure. But even with Kubernetes, a lot of these teams, they try to avoid the complexity, but they end up just shifting it, where instead of spending the time building out this infrastructure using Gitops, they have these manual deploy processes that don't work well. So you're probably asking, what is Gitops? Gitops is a set of best practices in which we use Git as our single source of truth. So every deployment, every workflow has to be born out of our Gitops as some sort of automation pipeline, like a CI/CD pipeline. So that way we can build in a vacuum and have consistent deployments one time after another, ensuring that reliability and the speed. We'll go ahead and get to the demo now. We're going to show how you could possibly deploy changes to a website with just a single click of a button. Okay, so here we are at Google, but you'll see this is actually running on my local host. This is not the real Google. It is a web app that I'm hosting on my own server. So if I come into my terminal here and I do kubectl get pods -a, this is my Kubernetes cluster that I'm running on my home lab. And what you notice inside of here, I have a few different things that are running, but the really important ones are Flux System. So we're using Flux CD here and Google. This is my web app that I'm running. And if I do k get service -n Google, you'll see here, this is a service that is hosting my application. So then if I do port forward, I can port forward this, and that's how I got it on my localhost 3000. So that's great, but that's nothing special, right? What we want to do now is I'm going to make a change to this Google web app, and it's going to jump over to this deployment without me having to do anything other than press one button. So I'm going to go ahead and open up my GitHub repository that has this application in it. And if I scroll over here, you'll see I have Helm/Google. So we're using a Helm chart to configure this. So we have some predefined templates that show the deployment and the service within Kubernetes. And so if I come over to my pull request here, you see I have this new button. And then inside of new button, you'll see there's two files changed, and one's a configuration and one is just adding in the new button. And then I will come over here and we're going to merge it into our main branch. So I'm going to go ahead and merge this. And now what happens when I merge this? We will see a GitHub action that kicks off here. And this GitHub action is going to package my web app inside of a Docker image. So I come back to my code base and I scroll down. I have a Docker file here that configures how this build should occur. Once this build occurs, we go ahead back to our code and come down to packages. We will create it as a GitHub package here, and you'll see it'll tag it as latest automatically. So we have a customize here, and there's a lot of infrastructure here, but the main thing that deploys Google is this customize file. It calls google.yaml. And then if I open that up, you'll see we configure a namespace. We configure the GitHub repository it's connecting to, which is this one here. And then we configure that Helm chart. So that Helm repository that I showed that has the service and the deployment. And what this does is based off this interval, which is every 1 minute, it's going to go ahead and check and say, hey, do you have any updates for me? Do you have any updates for me? And when it does, it will take those changes and reconcile them and put them in the cluster just off of the pull request. Okay, so now let's head back to our terminal and check on our pod. So we do k get pod -n Google. And we'll see here, this one's been running for 15 seconds. So it deleted the old one and it created a new one from that new image. So let's go ahead and check our packages. And we'll see that request completed. If I go over here to Google, there was latest created 5 minutes ago. So now that's running. And let's go ahead and do port forward. And then let's open back up our browser and go to localhost 3000. And there we go. Subscribe has now been added. Okay, so hopefully by that demo, you can see what Gitops is and why it exists. A quick rundown on the Gitops principles. So we want to build declarative infrastructure that is stored in Git, and then Git is used as our source of truth that everything is pulled from. We then configure automated reconciliation to ensure that the systems match that desired state. So what that means is that we configure that desired state as Git, which in this case would be our Kubernetes cluster, our Helm chart, those sorts of setups. And then we reconcile that state with something like Flux CD, which automatically makes those changes. So Flux CD reaches out to our GitHub and says, hey, have you made any changes? Is there anything I need to do? And GitHub comes back and says, yes, actually, there was just a new release 30 seconds ago. And then Flux CD pulls in that new release and makes the changes required to now match the system to that state that we defined. And there's a couple other things to it, like the CI/CD. So that's the Git action. I went through it very quickly. But what we did there is we defined a way to build within a vacuum so that everything is consistent. The problem is the way things used to work is that some developer would be pushing their stuff to prod. I mean, statistically speaking, with the number of people watching this video, there's probably going to be someone that SSHs into their machine to deploy their application to prod. And so this still happens today. What we're solving for here is that difference between machines. So when one developer says it works on my machine and the other developer says they can't, we're creating a centrally managed workflow that always handles that. So it's not, did it work on your machine or your machine? It's, did it work and get tested in the pipeline? We have a pipeline that is always the exact same. And if that breaks, it's because someone built it wrong. It's not because the machine didn't have the right setup. And that building inside of a vacuum allows us to ensure the consistency before we make those pushes, which is why we can be confident in systems like this where it automatically deploys as soon as we merge. This demo doesn't have it to show, but you would usually have multiple environments and some other testing in place to make sure that things work in the lower environments, and then the prod can just be a flip of a switch.
So how to use these practices? I know I went through a lot of this very quickly. This has taken me a long time to learn all of this, and I could never show all of it in one video. But I hope it gave you the idea of what teams at high levels are doing to work through. And it's way more than this even. But I hope this gave you a little bit of insight to the way these companies like Google work. I've learned most of this on my own through working with other people. And a big resource has been Google's Site Reliability Engineer docs. It's a whole handbook on how site reliability engineers, which it's a type of DevOps engineer, if you're not familiar, basically. They have a whole handbook on how they need to be thinking about these problems and solving them. And it's a great resource for anyone trying to learn. I'll link that down below for you. Now, of course, most of you guys are not going to be at Google or a company the size of Google, but these best practices scale all the way down. You might not need to build things out exactly the way that they would, but thinking these practices first and implementing them from the start is the best way to do it. Because once you start a project, it's really hard to go back and build this type of reliability in. Whereas if you think about it at the forefront, that's where you can get these systems that scale extremely well. A couple quick wins that come from this is that we get very easy deployments. So like I said at the start, there's no fighting over, oh, it's my turn to test or it's the other team's. We can create these deployments and have them happen as soon as the developer makes a change, and which gives them that instant feedback loop of whether or not the change works so that they can fix it as quickly as possible from the time that they wrote the code. It also allows us to roll back changes very easily. So if you deploy something that has a bug in it, we can just go pick out the Git commit and revert it, and it'll automatically deploy again. And the other one's the scalability. It's really easy to get in with this once you understand it and just start making change and feel very safe about that change. The worst thing is getting into a company where you have only a production environment and you have one chance to deploy and you have to manually roll it back. And it's kind of very scary to make that change because if it goes wrong, you don't have the best way to get out of it easily. So if this got you interested in GitOps, here's the way that I would get started on it. The first thing I would do is learn tools like Terraform. I know I've already preached this on this channel in the few videos that I've put out, but Terraform is a declarative infrastructure that you can define as code, and then you can build in CI/CD like GitHub Actions or automated deployments through Terraform Cloud. That way you can get used to the workflow of writing code, testing it, and then pushing it to Git and deploying from Git. The goal here is to get off of our command line and off of our personal machine and make sure that anytime we're making changes, it's done from Git. Start out small, start using tools like GitHub Actions. Just go find a piece of code that you've written, whatever language it's in, add a linter to make sure that things are structured properly. Add your build pipeline. So if you have a React application, set up a build pipeline in a Docker container and then put that on a GitHub action. And that'll give you a really good baseline to learn how the releases work, because the release is really important here and learning how to structure that and the flow of the code. After you're comfortable with GitHub Actions and Docker, I would go try to learn Kubernetes. Start out small, just spin up something light and find a project that you can follow along. I have some on this channel, not to plug them, but go check that out. And you can do this you can download Rancher OS, you can download Rancher Desktop, you can download K3S on a laptop like I did for my home lab, or you can use one of the cloud providers to spin something up and then delete it when you're done. After you've learned those baseline skills, then you can get into tools like Argo CD and Flux. Argo CD and Flux are both used in the same way. It's just which one do you want to pick, and there's benefits to each. These tools are a lot of fun to learn when you get started with them, and it'll kind of open your mind up to new projects and how you can deploy things and how you can set this and make things better at your work. These practices can be hard to justify because it's a lot of upfront work, but it saves so much tech debt in the end that it makes the workflow so much easier and makes the dev and the ops team both happy, which is always the goal of a DevOps. Quick disclaimer on this. I'm running this off my home lab, like I said, which is just that little server that I showed. So obviously this is not a Google deployment and they have much larger scale infrastructure than I'm doing here. There's a lot more complexity in their system. And the other thing is they might have different tools in-house. So I know they use Kubernetes because they built it, but I don't know if they use FluxCD or Argo. They probably have an in-house tool if I had to guess, but all of the principles still apply. So if you made it this far in the video, I'd really recommend reading that Google SRE documentation. It has changed my thought process and helped me learn so much.
So first, I'm going to show you the infrastructure that I've built. So we're going to have 3 servers on AWS we'll connect to. I'll show you that we can SSH into them, and then I'll show you how that translates into Ansible and what Ansible does. And then lastly, we'll actually build out a task and show you how we can run Ansible on all 3 servers at a single time. Okay, so here we are in the AWS portal. And what you'll see here, if I quickly refresh, we have 3 instances that are currently running. So we have dev instance 1, 2, and 3. These are all just T2 micros that I set up an SSH key pair on, and I'm using the latest Linux AMI. So nothing special about these. I'll include the code in the description. So I'll put some documentation in the README. This is Terraform. I'm actually working on something else with this. But the Terraform here, it just builds out a network, the different parts of the network that are required, and then this main.tf file will call the network. It'll get the latest AMI, and then it will provision these instances. So down here is where the instances actually get created. One note, this is using my SSH key pair. So make sure that if you are using this and you want to go and do this demo yourself, change out this key to be your own SSH public key. But you can also build out these servers manually. I just like using Terraform because it's a little bit easier for myself. So getting back over here now to the Ansible, if we go in, first thing I want to show, we do have this ansible.cfg file. This is just a configuration file. That's the default location to look into. So just wanted to point out we are using Python 3 as the interpreter, and I turned off host key checking. Now to get into what we're actually going to do, Ansible is like SSHing into multiple clients at a single time. So if I actually open up one of our EC2 instances here, I'm going to go into this one. I will copy, if I actually go into connect, and then I copy this command. So I'll paste this in, and I'm actually going to change out this. So instead of using this local ID RSA, I just want it to use my default RSA file. So if I just remove that, it should do it. And there we go. So now we're on the server. And if you see here, I mean, there's nothing in here. We're logged in as EC2 user. Again, I have not done anything to this server. So if I wanted to come in here and say sudo yum update, then I would have to do it in every single server. Whereas with Ansible, we can do it with all of them at once by defining that configuration or the playbook as code and then running that code against all of them. So now how do we compile that list of servers? That's going to be our host file. So I come back here, I have this host.ini file. And what you'll see here, we have a group and then we have our server. So I could come in here, all will literally do everything in this file. I could also say web servers, and then I could also say API servers. So then this way, I'll actually grab out of here now. We're going to go get all 3 server IPs. So here is one IP. Let's check. This might be the one I already have. It is. Okay. So let's go grab the other 2. So if I go back, this is instance 3. Let's go down to instance 1, grab that IP, go ahead and paste this in here, and then go back and let's get the last one. Instance 2, copy that, and bring it over. So now, these obviously don't have anything web server or API server related, but this is how we group the servers. Now, the other thing you've probably noticed is this configuration here. So Ansible, again, it's just underlying using SSH. So it's looking for an Ansible user that is the user that you're SSHing with. So if I open this up, you'll see actually EC2 user is how I SSH'd. The IP is right here. That's the value we set. And then Ansible SSH private key file. This is the location on my local machine where that file is stored. So I'm going to just copy this configuration over for these as well. And if you have everything the same, I could actually set this in my ansible.config file if it's generic for all of them. If you do have different configurations for any reason, like let's say this one wanted to connect with a root user, I could change this here and have a different configuration. I'm just going to leave it like this for now because this will work. So now what we have here, we have an all list, which includes this server. It includes all web servers, so the 3.101, and then it also includes the API servers. But if I call web servers, it will only include this host. And likewise, if I call API servers, it'll only include this host. So knowing that, let's get into actually building out our first run of this. So I'm just going to do hello world.yaml. And starting in here, always want to have 3 ticks up top to cover it. And that's just syntax of Ansible. Then I'm going to give my task a name. And of course, Copilot's prompting me. Let's ignore that. So I'm going to do hello world hosts. So this is offering localhost. That would be running on the machine where I actually run Ansible, meaning my Mac that I'm on right now. I don't want that. I want to, let's do all to start. And then moving down, now we will define the tasks that are to be run inside of this play. So you'll see here, I will just take this. It's going to print hello world. One thing I do want to change, though, I don't want this to be a bug. I want it to be a built-in shell. Built-in .shell. And then we will add echo in front of this. So now this is saying run a shell on the machine that we're connecting to, and then that shell will run echo hello world. So let's go ahead and test this out. We will do, if I run Ansible here, I should have it. So what you'll notice in this command, I'm running Ansible -playbook. That's the command to invoke it. -I will give the host here. So I'm setting host, and I actually need to add .ini here. So this is the host file we want to reference, and then the file name of the playbook that we want to run, and that will be hello world.yaml here. So I'm going to go ahead and run this, and you'll see it'll gather facts by default. So Ansible will automatically do what's called gathering facts. That is basically finding like what's the host name of this server, what's the operating system is running. You can go look in the documentation. There's a ton of details it'll give you. One thing to note, that does slow things down. So if you want to avoid that, which sometimes there are cases you want to, you can do gather facts no. But if we look here, you'll see it just says changed on all of these. So it ran these tasks and it's saying we ran print hello world and it changed because something happened, but we didn't debug or log the output, so we can't see it here. So we could add in the debug, but what I'm actually going to do is I'm going to write it to a file so that you can see that we have different files on each server. So I'm going to go ahead and change this to a built-in copy, and then it's actually going to do it for me. And so we can assume now this is going to write to temp hello world.txt on the file server. Before we do that, I want to add one other thing. So the other thing we can do is you can insert variables. This underneath the hood uses Jinja templating. So that's a common templating engine that's usually used with Python. So we can actually add in double curly braces here, and let's add inventory host name. So this is saying whatever host it's running on, put that in here as hello world from host name. So I'll actually add from here, and then we can go see this when I run it. So let's go ahead. We'll run the same command that we just did, and you'll see it's going to do, this time it won't gather facts because we turned that off. And now it's going to run print hello world, and again, we see changed. Now, if I SSH into my host again, let's go to temp/hello world. There we go. File exists. And we can see hello world from, and then our IP address. So that's how we just wrote to this host, and I can go check another one just to show that we're running on all of these. So let's copy out this IP here, go back to our SSH, and I'll replace that. And then I'm just going to copy that command out. And there's our file again. So we've now wrote a file to each of these servers. And so you can see it's just like as if I SSH'd into this server and then ran the command to echo hello world and put in the host name and catted it to the file. So that way we can automate it. I run it, I write the code to be run once, and then I can distribute to all of my servers. Now, the other thing I do want to show here, so let's go ahead and change this hosts up top, and we will do web servers. Actually, we're going to leave this the same, so our playbook will say hosts, but I'm going to add what's called a limit in our command. So I'll run this again to show you we can compare the outputs. So when we run this, pay attention, print hello world. Actually, good point. See how it says okay here? Last time it said changed. That file already exists, so we didn't change anything. So now it just says okay because it was already done. It's smart enough to know that. But what we see here, it ran against all three servers. So I'm going to add a limit to say which server out of my hosts I want to run. So it will have to exist in my host file, but out of these hosts, because we have all in the playbook, it gives me reference to all three of these servers. But then if I say, let's say 3.101 failed to connect or something, I can do -L, meaning limit, and put in the host name and then run it that way. And what you'll see here, we only run it against one host. So there's multiple ways to go about this. I could also do my group name here. So let's go ahead and delete this IP. And this time I will do my API servers. And there we go. We should see 52.53, which is our API servers, gets run. So limits are very important. This way, when you get into really large scale environments, you generally have inventories that are dynamically created, and then you use limits to reference the files that you need to.
I'm going to take you through the steps required to set up a cloud native Postgres database on a fresh Kubernetes cluster, and then we'll query that data with Prometheus and visualize it with Grafana. You should just take this as a starting point and then make changes to learn further. Links in the description as always. The README will walk you through the exact steps you need to get this set up to this point. Now that we're here, I'm going to go ahead and do k get pods -a to see if it's working. And it looks like we are. We're going to be using the cloud native PG operator, and this is the quick start guide. So to start it off, we already have our cluster. I'm going to go down to the install cloud native and that link here, and then just copy this command. This is going to apply a file from that GitHub user. Go back to the terminal, go ahead and apply. And now you'll see this is installing a bunch of CRDs or custom resource definitions for the Postgres operator. So now if I do k get crd-a, I'm going to grep this out. So if I do that and then cnpg, you can see all of these are the ones that were just installed. So now if I do k get pods, we also just set up a few pods running. So we have our cnpg system now running, and that's our controller. You'll see 20 seconds ago. Let's come back to our installation guide. Now that our operator is installed, we want to install a cluster. So here's this file. I actually saved this to GitHub already. So this will be in helm/cluster.yaml. So let's copy that command out. Actually, I can just do it. So let's go ahead and do k apply-f helm/cluster.yaml. There we go. Now our cluster's created. So if we do k get cluster-a, okay, so it's setting up our primary. So if I come into our file now, you'll see here, we have our kind here, which is going to be the cluster, the name's cluster example. We want 3 instances within this cluster. And the key here that we're going to be working with is the monitoring. Enable pod monitoring is true. This is going to enable the metrics on this cluster so that Prometheus can query it. So for those that aren't familiar, we have to enable our services to expose their metrics, and then Prometheus will query them and put them into a time series database. And that's how we can track this data and the change over time with our database. And then we use Grafana to visualize it from there. Okay, and if we look now, it's been a couple minutes. Our cluster has cluster example 1 through 3 running. So let's go back to Google now, and we're going to set up Prometheus next. In this quick start guide under part 4, we can go to monitor clusters. And if we scroll down here, we can copy out these 2 commands. So this is going to use Helm. If you don't have Helm already installed, make sure you get it. And this is going to add the Helm chart for Prometheus community, and then we'll install the Kubernetes stack, which is the industry standard for monitoring on Kubernetes. Okay, so it looks like Prometheus has been installed. Let's run this, and there we go. Here's our 2 pods that are running now. I'm going to do get pods-a to see everything that we have now. So we have these 4 pods running. It's initializing our Kubernetes here. And if we do k get service-a, we have. So now you'll see it installed community Grafana, alert manager, operator, Prometheus, and then state metrics. One of the key things to note here is that we passed in this file for our values file. This file is custom to the cloud native PG so that they already pre-configured the values.yaml for us to work with our cluster. Next step, we're going to go ahead and port forward our Prometheus. Just take out this command. And now it's going to port forward to 9090 on our local host. Okay, so I just went through this without hitting record on accident. So I'll go through it again quickly. We are going to go into our Prometheus now. And if we search for CNPG, we can now see everything, all the different options of data that query on that cloud native provider. So then I'll just pick one of these at random here. Let's do database bulk reads. And then I can execute that, and you'll see here. So this is that time series database of all the instances of this provisioning. So what you'll notice here is the container type is Postgres because that's what we're built on. And then we have the instance IP here. And notice that port is 9187. So on this port 9187, this pod is actually making these metrics available. And then Prometheus is querying it. And so that's really important because Prometheus is a pull model rather than a push. A lot of services like CloudWatch are push models where the service will push the logs, whereas this one is pulling, which means that if this service goes down, Prometheus is going to know right away that that's a problem. Now that we have our data configured, let's go ahead and use Grafana to query that data. So we're going to come down here and copy this command out. This is going to port forward the Grafana service. We come into our terminal, go ahead and port forward it. So when you get here, there's going to be a login page. The username is always going to be admin, and then the password is right here. It's prom operator. You can change this in your values.yaml. Make sure you don't leave that if you're doing this in a production environment. Go ahead and log in. And now here's our homepage. So Grafana is an open source dashboarding tool where you can configure dashboards and then export and import them as JSON files. And CMPG's already made a dashboard that we can import. So I'm going to come into my dashboards here, press new, press import, and then open up this file. It's a link here. And you can just copy this whole JSON and paste it into here. Here, it'll make our name, our folder, and then we'll want to select our Prometheus instance. So you should only have one. Go ahead and import. And now that we've imported this, you can see all of our data. So some of this is going to say no data because it's an old dashboard that they haven't maintained the best. But this is meant to be a first use case. So take this dashboard now, it's a template, and you can actually come in here and edit it. So we can change where these things are at, what data they're using. So each of these tiles is referencing something in Prometheus. So it's checking, is the cluster up? What's the max number of connections? What percent utilized is it? How long ago did it start? So all of that data is getting queried from Prometheus to the pods, and then Grafana queries Prometheus to get that data and then put it into this visualization. And you can change everything in Grafana. And so if we look here, we can see our 3 clusters here. Cluster with metrics 1, 2, and 3. They're all in the status up and they're replicating. Next up, we're going to create an alert. So I want to see if this metrics 1 goes down. I want to right click on this up tab, press more, and then go down to new alert role. So we're going to give it a name. We're going to call it metrics 1 down. And so you'll see here, this is the query. So I'm actually going to copy this over. So I copy this over to Prometheus and then run it. If you click on graph, then you can see it was down. And then at this point in time is when it went online. And now it's been online since then. Prometheus uses PromQL as their language. So you'll have to research that more if you want to make your own queries. Continuing down, we're going to leave all of this the same. Go to our evaluation. I'm going to add it to rules. Create a new eval group. And I'll do every 10 seconds. Instance down, I'll call it. So I want to know within 10 seconds if this goes down. Now you can configure an alert manager here. So you can set a contact point. Right now there's just default email, but you can view or create contact points. If I open this tab up, now inside of here, there are all kinds of integrations. There's AWS SNS, so many different things. You can just send an email to yourself. You can do Microsoft Teams. PagerDuty is one of the big ones. So we could send a PagerDuty that would call me if anything goes down. So for this though, I'm just going to leave it as the default and we'll come in here and view it, but you can imagine how that would go. So I'll set the default value and then message server 1 has gone offline. Runbook, we'll leave that. And let's go ahead and save and exit. So now we're going to go back to our alert rules page, open up our rule instance down here, and you'll see it's firing, which means it's actively running, and it evals every 10 seconds. And I'm going to come back to our terminal now and do k delete cluster.
And that ties up all the modules. So next up, we're going to go into our Capstone project. This project is going to combine everything that you just learned in this whole video and put it together into a single project that you can build out. You can use it on your resume. You can put it into your GitHub. And then that way you can also talk about it in interviews. One little tip also, I would recommend putting something on a YouTube channel and just show you talking about it and building it. That way you have real proof that you can actually send to people. So let's get into it. We're going to start with a fast API server with a few CRUD operations. Then we're going to put it inside of a Docker container. We're going to push our code to GitHub and use GitHub Actions to build that Docker container. We're going to then push that Docker container to a GitHub package registry. Next, we're going to use Terraform to build out our Kubernetes cluster on Azure. And lastly, we're going to import our GitHub package into our Kubernetes cluster. Okay, so we just finished up our fast API server. Let's get into it. This is going to be extremely basic. I wanted to make it really easy for you to jump in here and make changes yourself. So we're going to use just a local data store. One thing you could add in a database if you wanted to do that. There's a lot of things you could do to enhance this, and I would strongly recommend doing that.
our baseline here though, so we're just going to have an app, which is the fast API server, and then we define a class, which is the item, and it's going to have a name and a description. We create a store, which is a Python list, and then we have our 3 routes. So we have our get on the path items, we have a post on path items, and then we have a health check, which just returns status 200. The get request is just going to return whatever's in our store, and then the post request is going to append the item to the store and then return that item to say it's been added. And lastly, I included the 3 sample requests. The other important files here, we have our requirements.txt, and then I used a virtual environment to spin this up. And inside of the README, there's some documentation on how to get going. And now I'm going to move on to Docker. Okay, so we finished up the Docker file and the GitHub action to deploy it. So let's go through that quickly. Starting with the Docker file, this is the base one that comes with the documentation for Fast API. So we're going to use a Python 3.9 base image, set the working directory to the code directory, copy in our requirements.txt, install requirements, and then copy in our application. Then the last entry is the command, which we run the Fast API, and we put it on port 80. For interviews, this is a really important topic in case you get asked it. The order of a Docker file, which the lines are run, is important. The lines correspond to the layers of which the image is built. So you want to make sure that whatever's changing most frequently happens at the end. We put our requirements entry in before our application code because we know that our application code is going to have changes more frequently. So the image will cache anything that has not changed. So if our requirements don't change, we don't have to run pip install every time we build. We'll start immediately at this copy app command, so it makes it much faster. Whereas if I move this up top, and now I run copy app, and app has changes, every time app changes and I do a Docker build, it has to copy the code and then copy the requirements and do pip install every single time. In this sort of application, it doesn't really matter because we're installing 2 requirements, but when you get to Docker images that can be up to, say, a gigabyte, it can save a lot of time. Then with the GitHub action, I created the GitHub action called deploy images to GHCR. I found someone's template that I was able to use and make a few changes for us. I had to add this username variable. You'll see it's referenced down here as ghcr.io/ and then my username. So this would be jgeisler14, which is my GitHub handle, and then /DevOps Python, which is the repository name, and then we tag it with latest. I was hoping to use GitHub Actor as I defined up here, but that uses capitals and you can't have capitals inside of your tag. So we had to go this route. When you're building this yourself, make sure that you make that change in this file. Now over in GitHub, you can see the success because our GitHub action ran and was successful. I'm going to open the actions, and then if I go to the latest run here and open up push image, you can see this is our job running. It logs into the container registry, builds the image, and then pushes it to the registry. And then if we come back to the code tab, over here on the right side now, you see packages. I can click on DevOps Python. This is now a container registry that's storing my image so that I can pull it from other places. One important note, if you come over here to package settings, check this box so that you have admin. And then under inherited access, you're going to want to make sure that this is inherited. And this repository is public. If you don't have it public, you're going to have to set up a PAT token, which is a personal access token. So I would recommend making this public since it's a resume project anyway. You want people to come to your GitHub and see it. Now that that's done, we're going to get into the Terraform to build out our AKS cluster so that we can start using this. Okay, so working through the Terraform AKS cluster right now, I'm leaving this link in the README. This is an example from HashiCorp that I'm using to get started, and then I'm going to configure it to our needs. Coming into the code base, I'm working on applying it right now. So these are the commands to start. You'll run az login and then Terraform init and then Terraform apply. And let's see, it actually just finished applying. So I'll go through that in a minute. Open up our main.tf. This example uses a data block to pull in the Kubernetes cluster once it's built. We configure our 2 providers. So we need to configure the Kubernetes provider and the Azure RM. This is important. We're going to use Terraform to create our Kubernetes cluster, but then we're also going to use Terraform to manage the Kubernetes resources inside. That's why we have both of these providers. We have 2 modules here. So there is the Kubernetes module, which this just creates a local file. So when you run this, it will actually use your path that you're on and create a kube config. So you can see it's actually in here. I'm not going to click on that because it will have secrets inside of it. And then the AKS cluster, this is where we actually create our cluster. We're going to create a resource group using some variables and then create the cluster from the other. Then inside of that resource group, we'll provision the cluster. And the last thing I want to go through right now, we have some variables set up. So I'm using the location West US2 and your tenant ID and subscription ID. You're going to have to get these for yourself. They will be unique to your account. So make sure you pull your values and update either in this file or setting through environment variables for these to run. Now in the Azure portal, these will be the resource groups that you see when it's done building. One of these is the network watcher. That'll be automatic. The other one's managed by the Kubernetes cluster. We created this TFK8, so I'm going to open this one. And you'll see there's just our Kubernetes service inside of here. There's not too much to see here. You can see what size we set it to, which should be the smallest, so it's not going to be expensive. You can go through and check these out as you build it if you want to get familiar with everything in here, get familiar with but from here on out, we're going to access our cluster just from the CLI. Now to check access to our cluster, I'm going to go make sure everything's okay. First, we need to run export kubeconfig equals /kubeconfig. This will just overwrite your default kubeconfig file if you already have one set. Now I have kubectl alias to just k, so I'm going to run k get pods -a. And it looks like all of our pods are running. So we have Azure CNS, Azure IP, Cloud Node Manager, Core DNS, CSI, Connectivity Agent, kube Proxy, and the metric server. These are all of the default pods that will come with your Kubernetes cluster when you build it on Azure. Now we're going to get into configuring it ourselves. So it looks like we just got it working. Now you'll see our health endpoint is the status 200. If I come back to my terminal, here is our kubectl port forward, the API namespace, and the service. And then we're doing port 8080 to port 80. So let's do k get service -a. And here's the service we're referencing. And then we created a deployment, which creates these pods. So I'll do k get pods -n API. And here are the 3 API servers that we're now running. I'll show you guys the Terraform in just a second that we finished with that. First, let's go test our curl command. So if I come back to my VS Code, let's go ahead and copy this one out. And I'm going to go ahead and do curl. And you'll see there are no items right now. And then let's go ahead and curl this again. And now we just put an item in there with our post, curl it, and there's our item. Great. So this is working. Let's go through the Terraform. So yeah, this is working. It was actually pretty simple. Inside of our Kubernetes module, the main.tf here, I create the namespace for the API and then create a deployment. This deployment is called API deployment, references the metadata here. And then most of this stuff you can leave alone. Down here at the spec, so this is where we're pointing to the container. The image is now our GHCR. So this points directly to our GitHub package registry. I put in a variable username so you can enter in the variable.tf here. And it references DevOps Python. Make sure that matches your repository. And my tag is latest. The name is what is actually going to be named on the server. And then we specify some limits for the CPU and the memory. Lastly, we set up a liveliness probe. So this is why we set up that health check where we return a status of 200. That's to make sure that our service is working. And the great thing about Kubernetes is that if it dies, it will reconfigure it. So I'm going to show that quickly. K get pods -n API. And so let's see, 548 is how long these have been running. So I am just going to delete this. K delete pod -n API. There we go, pod deleted, and 2 seconds. It's already creating. So that's the benefit here. And those health probes also allow us to, we could put in some monitoring. So that would be a great extension of this application. If you want to set up some monitoring with Prometheus and Grafana and check the liveliness probe and then report back to it. Let's just check this one more time. And there we go. Status running 21 seconds ago. So now this is working. Moving down here, we have our API service. And this one's very basic. It just says go from take the service on port 80 and the target port is 80 because that's what we defined in our Docker file here. So the service is port 80, the target port is port 80, and then our service gets created. And so if I come over to my terminal, that is why this command here, just to explain it briefly, we're port forwarding the namespace API, and it's the service that's called API service. And we want to make a connection from our local host port 8080 into the service of port 80. And that's why when we run this, it moves it to our local host here. The last thing we're going to test now live, and I hope this works, is we are going to make some changes. So I want to show the CI/CD aspect of this, how we can make changes and how it automatically pulls. So I'm going to go ahead and do a live edition here, and I hope this works, of the, let's see, hello. Actually, yeah, let's do hello. And we'll change this to hello. And then this is going to return a message that says subscribe. Okay, so we're going to go ahead and push this code. So I already have it added. So I'm going to do git commit -m final push, git push. And then let's come over to our GitHub and see these changes. And so real quickly, while that's running, a quick note, make sure that you run Terraform destroy when you are done with this or when you're not using it, because that Kubernetes cluster will run up your cost on your cloud bill very quickly. So to show the current state that we're right now, we have our containers here. They have all been running for the one we deleted 6 minutes and the other ones are 12. If I go to localhost 8080/hello, you'll see it doesn't work. But our new image has just been built. So let's go back to our summary, come over to our code, come over to our packages. And then if we look, our latest has just been pushed as of 2 minutes ago. So let's check our pods again, see that they still have not been updated. So this is where something like Argo CD comes into play, which I'll put a card here for my video on that. We've defined our deployment to, by default, because it's using the latest tag, it will always pull the latest, but that only happens when it's created. So I'm going to go ahead and delete these now, delete all 3 of these this way. We can use something like Argo CD to do this automatically for us. So it would catch that change happened on our GitHub, and then it would trigger to delete the old pods and pull in the new ones. Now, all I had to do here was delete it, and it happens because I don't have Argo CD installed. But let's list out our pods again. And now you'll see they're all age 11 seconds. When this pod gets created, it pulls the latest from that GHC repository. We don't even have to do anything else besides that. So now if I go back to our local host, go to, oh, I need to port forward it. Let's go find that command. And it's running, and there we go.